Hello there and welcome to Science for Sleep, where curiosity settles in slowly and the big questions of the universe are invited to sit with us for a while as the rest of the world winds down. Tonight's quiet exploration takes us into a corner of physics that usually makes even seasoned scientists pause, not because it's loud or dramatic, but because it sits at the meeting point of ideas that rarely cooperate. It's a place where gravity becomes far stronger than it wants to be, where quantum rules stop behaving neatly, and where the smallest scales of reality stop acting small at all. If you've ever wondered what truly happens when something reaches the Planck mass, you're in exactly the right place, and we'll walk through it slowly, patiently, so the details don't rush your mind or stir anything awake that should be settling down. Before we drift too far into this strange territory, I'd love to know where you are tonight. Maybe you're curled up on a couch with dim lights around you, or resting in bed trying to settle your thoughts, or listening from a place that feels familiar and safe. Wherever you happen to be, what time is it in your part of the world right now? It's always interesting to think that as we talk about the smallest mass scale with real physical meaning, each of us is arriving here from a different moment, yet sharing this one together. And if this kind of gentle science helps you unwind or eases your mind at the end of the day, I'd be grateful if you tapped like or subscribed. It helps this calm space reach others who might appreciate a quieter way of learning. For now, let your focus drift towards something surprising. The Planck mass sounds like it should be tiny, especially because the Planck length and the Planck time are unbelievably small. But the Planck mass isn't tiny at all. It's about 20 micrograms. A grain of sand weighs more, but not that much more. 20 micrograms is something you could hold without noticing, a mass light enough to ride along on a small breeze. Yet in the world of particles, where electrons weigh trillions of times less than this, the Planck mass stands out like a boulder dropped into a pond. It's the threshold where our equations, which normally behave themselves when describing things much smaller or much larger, begin to strain. They don't break entirely, but they stop giving straightforward answers. They twist and wobble and argue with each other, because reaching the Planck mass means stepping into a regime where the universe, as we understand it, starts to resist being described cleanly. When physicists talk about the Planck mass, they're not pointing to a particle that definitely exists. They're pointing to a limit, a point where two major theories, each reliable in its own lane, collide in a zone neither can describe without help. On one side you have quantum mechanics, which handles small things with careful precision, mapping out probabilities and energies and interactions. On the other side you have gravity, described by general relativity, which governs the structure of space around massive objects and keeps planets in orbit with its steady pull. Normally these two frameworks ignore each other without trouble. Quantum mechanics handles the tiny, gravity handles the large, but the Planck mass sits between them in a space neither fully knows how to control. Imagine placing a particle on a scale. If the particle weighs as much as the Planck mass, the mathematics describing it suddenly makes gravity just as important as all the quantum forces combined. At smaller masses, gravity is so weak you can essentially forget about it. At larger masses, gravity dominates entirely. But at the Planck mass, both systems demand equal attention, and neither one is willing to take a step back. This is why things become complicated. The Planck mass isn't just a number, it's the point where nature stops choosing a side. The tricky part is that we've never directly observed something at the Planck mass behaving as a particle. We don't have experiments that can reach those energies. A particle that heavy would need absurd amounts of energy to produce in a particle accelerator, far beyond anything humans could dream of powering in the foreseeable future, so instead we look at equations, relationships between constants, hints hidden in the structure of physics. The Planck mass comes from combining three numbers: the speed of light, the gravitational constant, and Planck's constant. It's the only mass you can build from those three ingredients without adding anything else. That makes it significant. It marks a natural scale where the deep structure of the universe asserts itself. It says, here is where everything changes. One of the strangest things that happens near the Planck mass involves a question that sounds almost contradictory. Can something be so small, yet so massive, that space itself tightens around it? If you compress almost anything to a small enough volume, gravity can take over completely and create a black hole. But for extremely tiny masses like electrons or quarks, this never happens. They're too light. Gravity barely notices they're there. But if you try to pack something weighing the Planck mass into a region close to its own quantum size, gravity stops being quiet. It grows intense. It pushes back. Space folds inward. You might end up with something that behaves more like a miniature black hole than a normal particle, even though its mass is tiny by everyday standards. This balance point worries theorists. It's where the intuitive picture of particles moving through space becomes blurry. To understand why this balance is strange, imagine shrinking an object smaller and smaller. Normally, as something shrinks, its quantum behavior becomes more pronounced. The uncertainty in its position grows, but gravity gets stronger as mass gets concentrated. At the Planck mass, these two effects meet head-on. If the object shrinks further, gravity would try to create a horizon around it. If it expands, quantum effects weaken. This tension is part of the reason why discussions of the Planck mass often drift toward quantum gravity, a field that doesn't yet have a complete theory. Another important idea tied to the Planck mass is energy. According to the famous equation relating energy and mass, even a tiny mass can hold tremendous energy if it's concentrated in a small enough space. The Planck mass corresponds to such an extreme energy density that the vacuum, the very fabric of space, might not behave normally around it. Space could fluctuate more violently than usual. Forces might momentarily slip out of the roles they usually play. These aren't chaotic or mystical ideas. They're just consequences of equations struggling to keep their footing. The Planck mass is where mathematical consistency forces the entire structure of physics to adjust to avoid contradictions. While talking about something so exotic, it can be helpful to keep in mind that this number, 20 micrograms, is something you could casually wave through the air with your hand. It's not an impossible mass. It's not unreachable in everyday life. You could collect a speck of dust of that weight without any difficulty. What makes it extreme isn't its size. It's the requirement that this mass be compressed into an unimaginably small region, far smaller than atoms, far smaller than protons, smaller than anything we can probe directly. The contradiction between its ordinary mass and its extraordinary compactness creates the strange physics. Without that compression, 20 micrograms behaves like 20 micrograms. Put it in a tiny enough space, though, and the universe's most rigid rules begin to push against each other. This tension between scale and mass opens up another question researchers often explore when thinking about the Planck mass. If something reached that mass while still behaving as a particle, how would it move? Would it obey the uncertainty principle in the same smooth way electrons do? Would it follow a trajectory that could be measured? Or would gravity insist on altering the behavior, bending its path even over tiny distances? In practice, we don't have the tools to test these ideas directly, but simulations and theoretical work suggest that motion near the Planck mass becomes unpredictable. Not random in the everyday sense, but sensitive to aspects of space that normally don't change quickly. The particle might interact strongly with fluctuations in the vacuum. It might behave as if the geometry around it becomes uneven. These details are speculative, but they stem from attempts to reconcile general relativity and quantum mechanics. Thinking about how forces behave at this threshold leads naturally to the idea of unification. Many physicists hope that at very high energies, all fundamental forces might become different expressions of a single underlying principle. We see hints of this already. Electromagnetism and the weak nuclear force merge at higher energies. Strong force calculations behave differently when pushed far enough. Gravity, though, always stands apart. It refuses to blend. But near the Planck mass, gravity becomes strong enough that the idea of unification stops feeling hypothetical. It feels required. If every other force blends together under extreme conditions, gravity must join the conversation eventually. The Planck mass is the point where many think that could happen. It is, in a sense, the entrance to a region where the universe becomes more cohesive, less divided into separate rules for small and large, light and heavy, fast and slow. The idea that something could be heavy enough to demand a new theory, but still light enough to fit on the tip of a needle, is part of what makes the Planck mass so intriguing. It's a reminder that scale doesn't always match impact. Large things aren't always influential. Tiny things aren't always gentle. The Planck mass sits exactly at the crossroads where these expectations fail. It pulls us toward a deeper understanding not because we've seen it in action, but because its existence suggests that beneath our familiar physics lies a structure waiting to be explored more directly once technology allows. The place where mass meets mystery has always been a difficult boundary for physicists to describe, not because the mathematics is impossible to write down, but because the ideas that emerge refuse to fit into patterns we find comfortable. When dealing with familiar objects, even very small ones, the rules tend to behave in a predictable way. Mass pulls gently on space. Quantum effects influence position and momentum. The fields that make up the universe stay reasonably steady, but as soon as something approaches the Planck mass under the right conditions, the conversation between these pieces becomes louder, more complicated, and less willing to settle into clear roles. It's the kind of territory where equations hint at more than they can confidently explain, and our intuition finds very little to hold on to. To make sense of this, it helps to remember that mass doesn't only determine how heavy something feels, it also tells us how strongly that thing will interact with the structure of space around it. Everything with mass bends space by some amount, and that bending shapes how other objects move. Most of the time, the bending caused by a tiny mass is insignificant, so small that you would never notice it even with very sensitive instruments. But if you keep the mass small while concentrating it into a very tiny region, the space around it becomes less forgiving. It tightens, it curves, it reacts as though it's being pulled inward. And when the mass reaches the Planck scale, that reaction stops being subtle. It begins competing with the uncertainty and fluctuations that define quantum behavior. The difficulty in describing this comes partly from how the two main theories handle mass. Quantum mechanics treats mass as a property that influences how a particle moves and how it interacts with fields. It doesn't say anything about bending space. General relativity, on the other hand, treats mass as something that directly shapes the structure of reality. It doesn't focus on probabilities or wave functions. The two theories grew from very different assumptions and were developed to solve very different problems. When something reaches the Planck mass in a very small space, neither theory can stand alone. They overlap in a way that neither of them is built to handle fully. If you imagine trying to measure the position of something weighing the Planck mass, you run into an immediate conflict. Quantum mechanics requires you to accept uncertainty. You can make a measurement, but the more precisely you try to pin down a particle's location, the more you disrupt its momentum. That's normally manageable, it's part of everyday quantum behavior, but when the mass reaches the Planck scale, trying to confine it too tightly adds so much energy that space itself becomes involved. The attempt to measure the position could, in theory, collapse the region around the particle into a horizon. You would no longer be observing a simple quantum particle. You would be observing something that behaves like a very tiny black hole. The act of measuring becomes inseparable from the act of bending space. The idea that the act of looking could change the structure of space in such a dramatic way is unsettling, because it shows how closely observation and geometry might be linked at extreme scales. This is part of why the Planck mass is considered a signpost in theoretical physics. It marks the beginning of a region where the universe refuses to let you separate its components. Forces you usually treat as unrelated begin merging in their effects. Concepts that worked well in isolation begin interfering with each other, and the closer you push toward that threshold, the more this interference becomes the defining feature of the situation, rather than a small correction. One of the ways physicists try to understand this region is by thinking about how different forces change strength as energy increases. At everyday scales, the electromagnetic force, the strong nuclear force, and the weak nuclear force behave according to predictable patterns. Gravity sits far below them in strength, but as energy increases, these forces begin to shift. Their strengths don't stay constant. They evolve in ways described by long calculations and patterns observed in particle experiments. Several of them grow closer together as the scale increases. Gravity, though always weaker, begins rising more quickly than expected. By the time you reach the Planck mass, gravity refuses to remain in the background. It becomes strong enough that you have to treat it as a central player rather than a small influence. This change in its behaviour is one of the biggest clues that something deeper is happening at this scale. The Planck mass isn't only a boundary for mass itself, it's a boundary for energy density, curvature, and even the basic idea of measuring distances. If a particle reaches this mass while packed into a region close to the Planck length, then inside that region the geometry may not resemble the smooth, continuous picture we usually imagine. Instead, it may shift rapidly in response to the energy present there. General relativity predicts smooth curves, but near the Planck scale those curves might become uneven. Quantum mechanics predicts smooth wave behaviour, but that smoothness might break apart under extreme gravitational influence. The result is not chaos, but a picture of reality that is much harder to describe using familiar ideas. Another difficulty arises from the fact that the Planck mass is connected not only to energy and gravity, but also to the idea of action in the quantum sense. Planck's constant sets the scale for how quantum phenomena behave. When the mass reaches the Planck value, it corresponds to a point where quantum effects are no longer small corrections to classical behaviour. They become the behaviour, and at the same time, gravitational effects are no longer negligible. They also become dominant. The two effects collide in a way that suggests new structures in the underlying laws of physics. There are models attempting to describe what this region might look like. One of them imagines that space could become grainy, not in a literal sense, but in how measurements behave. Instead of positions forming smooth ranges, they might appear in steps so small that no instrument could detect them, but still important for maintaining consistency in the theory. This would prevent distances from becoming smaller than the Planck length. If something reaches the Planck mass, the region around it might resist further compression because the very concept of smaller stops having meaning. It's not that something physically blocks the way, it's that below that scale the mathematics stops describing anything that corresponds to physical space. Another way to think about the boundary is to consider what happens to time. Time usually flows smoothly when described through relativity or quantum mechanics, but at the Planck mass, when gravity becomes strong enough to change the pace of time and quantum effects become strong enough to influence the sequence of events, you end up with a situation where neither picture is stable on its own. Time may run slightly differently in small regions, not in a dramatic way, but enough to break the assumptions used in many equations. If time changes across tiny distances unpredictably, the movement of particles becomes harder to predict. You can't assume that the time inside the region behaves like the time outside it. This complicates every calculation involving motion, energy transfer, or field interactions. Yet another part of the puzzle involves how energy is stored. Normally energy in a region of space increases gradually as you add mass. But if the region becomes small enough, the energy begins affecting the region's shape rather than just occupying it. The Planck mass is the point where the energy is dense enough to reshape its surroundings by its presence alone. It doesn't merely sit inside space, it alters the space available to hold it. This feedback loop is one of the core hints that physics becomes inseparable from geometry at this boundary. There is also the problem of stability. A particle with the Planck mass stored in a region near the Planck length might not behave like a stable particle in the normal sense. It might evaporate through processes involving quantum tunneling and gravitational radiation, or it might persist longer than expected depending on how quantum gravity works. We don't have experimental data to settle these possibilities, but the theoretical work suggests that stability becomes a difficult idea to maintain when forces overlap so strongly. A particle might shift between different configurations faster than we can describe. The fields around it might pulse or oscillate in ways that don't match familiar patterns. One of the surprising things about this boundary is how quickly predictions begin to diverge. Slight changes in assumptions lead to very different outcomes. One theory might predict that a Planck mass object behaves like a miniature black hole almost immediately. Another might say it behaves like a heavy particle with unusual gravitational corrections. Yet another might suggest that it becomes something entirely new, neither a particle nor a black hole, but a structure that arises from a deeper framework we have not yet discovered. This variety of predictions shows how little we truly know about what controls behaviour at this scale. Even though this part of physics is filled with unknowns, it still guides researchers toward deeper questions. If all known forces become comparable near this mass, then understanding what happens there could reveal patterns linking them. If geometry behaves differently, it might point toward a unified description of space and fields, and if time becomes unstable in small regions, it could provide hints about whether time is a fundamental part of the universe or something that emerges from deeper relationships. The strange world hidden beneath the Planck scale is one of the most challenging regions of physics to imagine, not because it is chaotic or mystical, but because it doesn't behave in any way our usual expectations can handle. Everything we use to describe reality, distance, duration, mass, energy, motion, geometry, begins to lose the characteristics that make them familiar to us. It's not that they stop existing, they simply stop behaving in the way we understand. If the previous discussions focused on what happens as mass approaches the threshold, where gravity and quantum mechanics collide, the territory beneath the Planck scale is about what happens to space and time themselves before anything with mass even enters the picture. To understand this region, begin with the basic fact that the Planck scale is not a place you can reach by zooming in with a powerful microscope. It's not a tiny room waiting underneath smaller rooms. Below the size of atoms, there are electrons, protons, and quarks. Below quarks, there might be additional structure, or perhaps nothing more fundamental. But no matter how small you go, there is no smooth path that lets you march toward the Planck length as if shrinking through layers. The Planck scale is not the bottom of a stack. It is a limit, a point where the very concept of a stack collapses. The smallest distances we can meaningfully describe begin to lose their relevance. The idea of smaller loses clarity. Measurements stop behaving normally. Even the act of imagining the place becomes complicated, because imagination depends on continuity, and continuity may not exist down here. The Planck scale is defined using the speed of light, the gravitational constant and Planck's constant. When these three constants are combined in specific ways, they define natural units that describe the smallest meaningful time, the smallest meaningful length, and the mass scale where gravity and quantum behaviour must be treated with equal importance. Those units are not arbitrary. They represent the limits where current theories stop giving reliable answers. If you attempt to plug in numbers smaller than the Planck length, or shorter than the Planck time, what comes out is not a picture of deeper detail, but a picture of equations failing to produce physically meaningful results. It's similar to trying to divide by zero, not in outcome, but in the sense that the framework you are using stops offering valid quantities. When physicists say reality might become granular or discrete beneath this scale, they do not necessarily mean that space is made of little cubes or grains. Instead, they mean that trying to probe distances shorter than the Planck length introduces so much uncertainty and gravitational distortion that the idea of distance becomes unstable. A measurement would no longer return a consistent value. The region around the measurement would fluctuate. The tools you use to define the position of anything would influence the geometry in unpredictable ways. If you try to compress a particle to a region smaller than that limit, The energy required to localize it would distort the surrounding space to such an extreme degree that even the idea of a location becomes problematic. These problems don't arise because the universe is hostile to inquiry. They arise because the concepts we use to describe it were built around assumptions that break down when pushed too far. Space is assumed to be smooth. Time is assumed to be continuous. Forces are assumed to operate on a geometric background that stays unchanged by the act of measuring. None of these assumptions hold beneath the Planck scale. The smoothness disappears, the continuity collapses, the background no longer stays fixed. Everything depends on everything else, and nothing allows itself to be treated as independent. To get a sense of why these assumptions fail, imagine trying to measure a very small distance using a particle of light. The shorter the distance you want to measure, the higher the energy of the photon you need to send into that region. A low-energy photon has a long wavelength, so it cannot resolve tiny features. A high-energy photon has a short wavelength and can resolve smaller regions, but energy curves space. If you add too much energy into too small a region, you distort the geometry so much that the region shrinks, shifts, or collapses. This effect becomes unavoidable once you approach the Planck length. The act of measurement influences the structure you're trying to measure so strongly that it becomes impossible to separate the probe from the geometry. Beneath that scale, the very idea of a geometric region becomes unstable. This leads to one of the most significant challenges in physics: the possibility that space itself does not exist in a meaningful way at sub-Planck scales. That statement doesn't mean the universe ends there. It means the tools we use to describe space, coordinates, distances, continuity, geometry, stop matching physical reality. Many models attempt to describe what replaces them. Some describe a network of relationships rather than a smooth expanse. Others describe fields that take discrete values rather than continuous ones. Still others treat space as emergent rather than fundamental, something that appears only when many smaller pieces interact collectively. One idea proposed by several researchers is that beneath the Planck scale, space might behave like a fluctuating foam. This foam is not a physical substance, but a shorthand way of describing rapidly changing geometry. Instead of a smooth, static background, space may ripple, twist, fold, and reshape itself on extremely short timescales. These fluctuations would be so intense and so frequent that they would erase any consistent features. Trying to track an object through such a region would be impossible because the space it moves through would not stay fixed long enough for the motion to be defined. Even the act of assigning coordinates would lose meaning. A point in space would not be a stable location. It would be a brief configuration of geometry that shifts before you can track its existence in any reliable way. The consequences of this are not limited to distance. Time also becomes unstable at these scales. The Planck time represents the smallest interval we can meaningfully discuss. Beneath that interval, talking about before and after becomes difficult because the sequence of events may not be well defined. If space fluctuates violently, the rate at which time flows could vary from point to point, not in a noticeable way that creates dramatic distortions, but in a subtle way that removes the foundations needed to define a consistent timeline. If events cannot be ordered, then traditional physics breaks down completely. All of our theories rely on the idea that events occur in a sequence. Beneath the Planck scale, that sequence might lose its structure. Another surprising aspect of the sub-Planck region is the possibility that momentum and energy could behave differently from what we expect. In quantum mechanics, energy comes in discrete steps depending on the system. But beneath the Planck scale, the discreteness may not simply be a feature of particular systems. It may be an unavoidable constraint on reality. Some theories suggest that energy levels become so tightly restricted that only certain configurations of fields can exist. Other theories suggest that energy becomes so sensitive to geometry that mapping out the distribution becomes nearly impossible. and there are theories that propose the existence of new symmetries or constraints that only show themselves beneath the Planck scale. These ideas are not based on guesswork. They come from trying to extend our existing theories in ways that remain self-consistent. Every time physicists push general relativity or quantum mechanics into regions they were not designed to handle, the two theories begin contradicting each other unless new structures are introduced. These new structures are not optional. They are required for the equations to make sense at all. The Planck scale is the point where the structures both theories rely on begin to conflict. Beneath it, new structures must exist, or the equations collapse. Theories like loop quantum gravity try to describe this by suggesting that space is made of finite units, that areas and volumes cannot shrink indefinitely. According to this view, space itself has a smallest possible unit, not because something physical blocks further shrinking, but because shrinking further becomes a meaningless operation. String theory, by contrast, suggests that what we call particles are tiny, vibrating strings, and beneath the Planck scale lies the size of these strings. In this theory, there is no need to talk about distances shorter than a string. Trying to do so would be equivalent to trying to describe the shape of a point on a violin string that no longer corresponds to its physical nature. Both theories aim to resolve the same problem. Beneath the Planck scale, our current descriptions of space and matter stop being appropriate. While these theories differ, they share one important message. Beneath the Planck scale, reality does not behave like a smooth surface or a continuous field. It behaves in a way that forces us to rethink what location and duration mean. Perhaps the most fascinating part of this is that the strange behaviour is not a sign of something unnatural, but a sign that our familiar ideas are limited. Much like classical mechanics loses accuracy when dealing with electrons, our current understanding loses accuracy when dealing with the Planck scale. It's not that the strange world beneath this scale is chaotic. It is simply governed by rules we haven't fully uncovered. This strange territory also influences how we think about the origin of the universe. If the early universe was once compressed into a region smaller than the Planck length, then its earliest moments were governed by the sub-Planck structure. The fluctuations, the unstable geometry, the unpredictable sequence of events, all of these may have played a role in shaping the universe we now observe. This suggests that understanding the sub-Planck world is not merely an academic question. It may be central to explaining the universe's structure, the distribution of matter, and the emergence of the forces we know today. Exploring this region also raises questions about whether space and time are fundamental, or whether they emerge from something deeper. If the fabric of space becomes unstable beneath the Planck scale, perhaps the true constituents of the universe are not spatial at all. They may be mathematical relationships, fields without geometry, or structures that do not map onto space until larger scales bring order. This idea challenges our assumptions, but it is not unusual in science. Many familiar concepts emerge from deeper structures. Heat emerges from motion. Pressure emerges from collisions. Space and time may emerge from something we do not yet recognize. When people first hear the phrase Planck mass, they often expect it to refer to something unimaginably tiny, especially because it is defined alongside quantities like the Planck length and the Planck time, which are so small that many of our instruments could never hope to detect them. The Planck length is far smaller than the size of a proton, and the Planck time is so short that even light cannot travel a meaningful distance during it. So it feels natural to assume that the Planck mass must follow the same pattern. It should, in theory, be one of the smallest masses nature allows, but instead it turns out to be surprisingly large compared to the masses of particles we know. It is far heavier than an electron, far heavier than a proton, and even heavier than many biological cells. It seems completely out of place among the smallest building blocks of matter. To make sense of this unusual size, it helps to remember that the Planck mass is not describing an object we can hold or observe. It's describing a point where different pieces of physics collide. In many ways, it isn't a measure of how heavy something is. It's a measure of how much mass needs to be squeezed into a region so small that the normal rules break down. That requirement produces a number far larger than most people expect. Even though the Planck mass is only about 20 micrograms, that amount is enormous in particle physics. Most particles have masses measured in electron volts or giga-electron volts. If you compare them, the Planck mass corresponds to an energy scale so massive that our accelerators cannot reach it. Not because the mass itself is large in human terms, but because a mass that big, when concentrated into a quantum-sized region, creates conditions that bend the structure of space. This contrast between what seems small and what behaves large is one of the reasons the Planck mass stands out. In everyday experience, 20 micrograms is hardly noticeable. A dust particle weighs about that much. You could carry it without realizing it existed. But the Planck mass lives at the intersection of gravity and quantum mechanics, and that intersection magnifies the effects of even a tiny amount of matter. When you place a mass into a region that is shrinking toward the Planck length, the behavior of the system becomes dominated by gravity in a way we never encounter in daily life. To appreciate why this happens, consider how gravity normally behaves at small scales. For particles like electrons or quarks, gravity is so weak that it can be ignored. The electromagnetic force, the strong nuclear force, and the weak nuclear force completely overshadow it. Even though general relativity tells us that mass bends space, the amount of bending caused by a single electron is negligible. If you were to calculate the curvature around it, the result would be so small that it would be meaningless for any practical discussion. But this picture begins to change when you look at what happens if a mass becomes extremely concentrated. Gravity becomes stronger, not because the mass is large, but because the density becomes extreme. When you push mass into a small enough region, the curvature grows. At everyday densities, this effect barely registers. At nuclear densities, it becomes measurable. At densities where the Planck mass is contained within a region approaching the Planck length, gravity becomes unavoidable. This is the key reason the Planck mass behaves so strangely. It represents a point where quantum density and gravitational curvature influence each other so strongly that you can no longer separate them. There is another reason the Planck mass feels unexpectedly big. It arises from combining three constants that each carry their own scale of meaning. The speed of light sets the relationship between energy and mass. Planck's constant sets the scale at which quantum mechanics becomes significant. The gravitational constant sets the strength of gravity. When you combine these three, you get a mass scale that balances gravity against quantum effects. It's not small because gravity is weak. To make the two match, the mass has to be large enough that gravity's influence becomes comparable to quantum uncertainty. This point of balance is important. Quantum mechanics describes how particles behave at small scales, where uncertainty plays a central role. General relativity describes how mass bends the structure of space. The Planck mass is the point where uncertainty and curvature become equal players. If you try to shrink a mass below a certain size, the energy associated with the uncertainty principle increases. At the Planck mass, that energy becomes strong enough to curve space significantly. It may even become strong enough to form a horizon. This suggests that below a certain length scale, gravity stops being a gentle background force and becomes a central component of particle behavior. This raises an interesting question. If the Planck mass is so large compared to particle masses, why don't we see any particles near that mass in nature? The simplest answer is that they would be unstable in the environments we know. A particle with the Planck mass compressed into a region approaching the Planck length might collapse into a tiny black hole, or it might evaporate quickly through quantum processes, or it might exist only briefly in the early universe when energies were much higher. Because of this, the Planck mass is not represented by objects around us. It represents a boundary in the structure of physics. It tells us when new effects must appear, even if we cannot observe them directly. Some researchers have proposed that objects near the Planck mass may have existed in the early universe. The universe was once far denser and hotter than anything we can create now, and conditions may have allowed particles or structures with masses near the Planck scale to form naturally. If they did form, they may have evaporated quickly or merged into larger structures. We don't have direct evidence of them, but their existence is not impossible. They might even play a role in discussions of primordial black holes, though this remains a topic of active study rather than settled understanding. Another surprising aspect of the Planck mass is how it compares to the masses of everyday objects. If you convert it into energy, the number is enormous. The energy associated with the Planck mass is far beyond anything a human-made accelerator could produce. So although the mass feels tiny in human terms, the energy behind it belongs to an entirely different category. This is why physicists describe it as a fundamental scale. It has nothing to do with convenience or human experience. It arises from the structure of the universe itself. What makes the Planck mass even more interesting is how its definition relates to length. When physicists define the Planck length, they are not describing a physical boundary or a minimum size in a literal sense. They are describing a scale at which quantum fluctuations in space become so strong that trying to define smaller distances becomes meaningless. The Planck mass is the mass whose gravitational radius is roughly equal to the Planck length. If you take an object with the Planck mass and try to confine it within a region equal to its gravitational radius, you approach the point where a horizon might form. This connection between mass and length is why the Planck mass feels much larger than the Planck length would suggest. The Planck length is small because it describes a tiny region of space. The Planck mass is large because fitting that mass into such a tiny region creates extreme curvature. It also helps to consider the role of units. The Planck mass is defined using natural units where certain constants are set to 1. In those units, the speed of light, Planck's constant, and the gravitational constant become dimensionless. The mass, length, and time that arise from these units are not arbitrary. They represent points where the underlying equations become simpler. If you write Newton's constant as 1, then the Planck mass becomes the natural mass scale for quantum gravity. This is why many theories that attempt to unify quantum mechanics and gravity treat the Planck mass as the fundamental scale, even if no particles correspond to it directly. One of the unintuitive features of the Planck mass is that it marks the only point where gravitational effects on a particle become comparable to other interactions. Below this mass, gravity is negligible. Above it, gravity dominates. At exactly this mass, the two are comparable, but this doesn't mean that particles must have this mass. It simply means that if a particle did have it, the theoretical description would have to include both quantum and gravitational effects in equal measure. This reinforces the idea that the Planck mass is not a particle property. It is a property of the structure of physics. It tells us how much mass you would need to force gravity into direct competition with the uncertainty principle. And this requirement leads naturally to a number that feels large compared to the masses of particles we know. There are also practical considerations that make the Planck mass difficult to incorporate into everyday physics. We have no way to produce such masses in small enough regions to observe their behaviour. Even if we could gather 20 micrograms of material, confining it into a region small enough to reach the Planck density is impossible with current technology. The pressures and energies required far exceed anything we can generate. This means the Planck mass exists mostly as a theoretical anchor. It shapes the structure of models but does not appear as an observable particle. Another point worth mentioning is that some theories propose modifications to gravity at very small scales. If gravity becomes stronger or behaves differently at short distances, the Planck mass might shift. Some models suggest a lower effective Planck mass in extra-dimensional theories. In these models, gravity becomes strong at much lower energies because the field lines can spread into more dimensions. If this is true, the Planck mass as we know it might not be the true threshold for quantum gravity, but these ideas remain speculative and have not been confirmed experimentally. The significance of the Planck mass becomes clearer when you consider how it influences the hierarchy problem in particle physics. The question is simple: why is gravity so weak compared to the other forces? The Planck mass sets the scale at which gravity becomes strong, but the masses of particles we know are far smaller. The difference between the Planck mass and the electroweak scale is enormous. Understanding why these scales differ is one of the central goals of modern physics. Some theories propose the existence of new particles or symmetries that explain this gap. Others propose new dimensions or changes in the vacuum structure of space, but no theory has yet been confirmed. The Planck mass also highlights how our understanding of mass itself is incomplete. We often think of mass as a simple quantity, something that tells us how heavy an object feels. But mass is more complex than that. It relates to inertia, to energy, to how an object interacts with fields, and to how it shapes the geometry of space. The Planck mass shows that mass is not merely an attribute of particles. It is a scale that emerges from the structure of the universe. The idea that the universe may eventually reveal a single unified description of all forces has been one of the strongest motivations behind modern theoretical physics. Long before anyone began discussing concepts like the Planck scale, or the strange territory where gravity and quantum mechanics overlap, physicists noticed something remarkable about the world around us. The forces that shape everything we experience are not scattered randomly across nature. They appear instead as pieces of a larger puzzle, as if each force is one expression of a deeper relationship waiting to be uncovered. This is what makes the Planck mass so interesting. It doesn't only represent a scale where gravity becomes as strong as the other forces, it represents a point where the universe begins encouraging us quite forcefully to consider the possibility that all the forces we know might once have been unified. To understand why this idea matters, it helps to begin with what we mean by a force in physical terms. A force is not only something that pushes or pulls, it is a rule for how matter interacts. It dictates how particles move, how they exchange momentum, how they attract or repel each other, and how the structure of the universe is maintained. In everyday life, we deal mostly with gravity and electromagnetism. Gravity keeps our feet on the ground and shapes the motion of planets. Electromagnetism controls everything from lighting in a room to the stability of atoms. But beneath these, there are two other fundamental forces: the strong nuclear force and the weak nuclear force. Each has a role in the structure of matter, and each has its own mathematical description. What makes these forces interesting is not only that they exist, but that they behave in systematic ways. They don't drift without pattern. They change strength depending on energy, and these changes follow predictable curves. This is one of the most striking hints in physics that the forces may not be independent after all. When you plot how the strengths of the forces evolve as energy increases, they begin to move closer together. At low energies, they are very different. At higher energies, their behavior grows similar. This gradual merging suggests that at an extremely high energy scale they may converge. The energy scale where this convergence might occur is far above anything we can produce in an experiment, but it is not infinitely high. It is large in a way that fits naturally with the Planck mass. The Planck mass represents the energy scale where gravity becomes relevant in particle behavior, and if all the other forces converge at some high energy scale, then gravity must join that convergence eventually, or the picture would remain incomplete. This is why physicists often talk about the Planck scale as a place where unification may occur, not because we have evidence that it does occur there, but because the behavior of the forces points toward a relationship that becomes unavoidable at that scale. To see how these forces might unify, consider how each force is described mathematically. Electromagnetism is described by a gauge field that interacts with charged particles. The weak force is described by a similar field but with different properties. The strong force is described by a more complex field that binds quarks together inside protons and neutrons. Each field has its own coupling constant that defines its strength. When you increase the energy of a system, these coupling constants shift. The equations describing how they shift are well understood and have been confirmed experimentally. As energy rises, the strengths begin to move closer to each other, as if they were different branches of the same underlying rule. This behaviour is not accidental. It emerges naturally from the mathematical structure of quantum field theory. The forces change strength because virtual particles interact with each other, altering how particles appear to behave at different energies. As energy increases, these interactions explore more of the structure of the fields, revealing patterns that were invisible at lower energies. The fact that these patterns hint at unification is one of the strongest pieces of indirect evidence that the forces may indeed have a shared origin. Gravity, however, remains separate in this discussion. It behaves differently from the other forces. Instead of being described by a gauge field, it is described by the curvature of space. Instead of acting through particle exchange at small scales, it acts through geometry. This difference makes unification challenging. But the Planck mass represents the scale where gravity is no longer negligible. It becomes strong enough to influence particle behaviour. This suggests that gravity too may have a quantum description that only becomes visible at extreme energies. One way researchers have tried to unify the forces is by proposing that the familiar forces we see around us are fragments of a single field. At very high energies, this field would behave in a symmetric way. As the universe cooled, the symmetry would break, causing the field to separate into distinct components. These components would appear as different forces. This symmetry breaking is not a new idea. It already occurs within the Standard Model. Electromagnetism and the weak force are unified into a single electroweak force at high energies. Only as the universe cooled did they separate, giving us the familiar electromagnetic force and weak nuclear force we see today. If two forces in the Standard Model already unify at high energies, it is natural to wonder whether the strong force might join this unification at even higher energies, and many theories suggest that it does. These theories are often called grand unification theories. They propose that at extremely high energies, all forces except gravity merge. The equations that describe these unified forces are more compact and symmetric than the equations that describe the Standard Model alone. They represent a more elegant description of nature, but elegance is not enough. Any unification theory must also match the behaviour of the forces we observe today. This requires calculating how the unified force breaks apart as energy decreases, and ensuring that the breaking pattern matches the Standard Model. Some theories accomplish this, others do not. Even the theories that do accomplish this face challenges, including the prediction of particles that we have not observed. Still, the success of the electroweak unification suggests that grand unification is not an unreasonable direction for physics to explore. But even grand unification leaves gravity out. The Planck mass is important because it represents the point where gravity is no longer optional. If a unification theory is to be complete, gravity must eventually be included. This inclusion is difficult because gravity's mathematical structure differs from that of the other forces, but the difficulty does not mean it is impossible. It simply means that our current mathematical tools are not yet adequate. The connection between the Planck mass and unification becomes clearer when you consider how quantum field theories behave near that scale. At low energies, quantum field theories work extremely well. At higher energies, they remain reliable. But near the Planck scale, the calculations begin to fail, the interactions become too strong, the approximations break down. This failure suggests that a deeper theory must take over. A theory that does not rely on the separation of forces, a theory that treats space, time, matter, and forces as parts of one structure. String theory offers one possible framework for this. In string theory, particles are not points. They are vibrating loops or segments of string. The different vibrations correspond to different particles. The forces emerge from how strings interact. Gravity arises naturally from one of the vibrations of the string. This is important because it means gravity is not added separately. It comes out automatically. This makes string theory one of the few frameworks that naturally includes gravity at the quantum level. Another approach is loop quantum gravity, which begins with the structure of space itself. Instead of treating space as continuous, it treats it as built from discrete units of area and volume. These units interact according to specific rules. Gravity arises from how these units connect. Unlike string theory, loop quantum gravity does not attempt to unify all forces, but it does attempt to describe gravity in a way that is compatible with quantum mechanics. Whether it can be extended to include other forces is still an open question. There are many other ideas as well, including asymptotic safety, non-commutative geometry, causal dynamical triangulations, and theories that propose additional spatial dimensions. Each approach has strengths and weaknesses. None has yet been confirmed by experiment, but they all share the same underlying motivation: the belief that at the Planck scale the universe behaves in a more unified way than it does at larger scales. The early universe provides additional hints. When the universe first formed, it was extremely hot and dense. The energy levels were far above anything we can create now. If unification occurred at high energies, then the early universe would have passed through a phase where all forces were unified. As it expanded and cooled, the symmetries would have broken, producing the forces we see today. This means unification is not merely a mathematical curiosity. It may be part of cosmic history. Understanding unification is also important for explaining the distribution of matter and energy in the universe. If the early universe underwent symmetry breaking, the patterns of this breaking could influence the structure of space, the abundance of particles, and the existence of cosmic phenomena such as inflation. Some inflation models rely on fields that could be connected to unified forces. Others draw on ideas that emerge from string theory. This does not mean unification has been proven. It simply means the concept fits naturally into several aspects of cosmology. The Planck mass becomes significant here because it marks the scale where gravitational effects would have been unavoidable in the early universe. If all forces were unified, then gravity must have played a role in this unification. This strengthens the case that unification theories should include gravity rather than treating it separately. It also raises the possibility that the force we call gravity is not a fundamental force at all. It might be an emergent property of something deeper. Some theories propose that gravity emerges from the statistical behavior of more fundamental components of the universe. If this is true, then the Planck mass is not a fundamental boundary. It is a transition point where gravity's emergent behavior becomes significant enough to influence particle interactions. Another clue that unification might be real comes from the way particles are grouped into families. The Standard Model contains several sets of particles that appear in repeating patterns. The arrangement is orderly in a way that suggests a deeper structure beneath it. Unification theories often predict these patterns automatically. This makes them appealing, though not definitive. The quest for unification is more than an attempt to simplify the universe. It is an attempt to understand why the universe behaves with such consistency across enormous differences in scale. The same rules govern atomic interactions and galaxy collisions. The same constants appear in equations describing different fields. The Planck mass represents a point where these rules may be different, and where the deeper structure might reveal itself. Gravity's place in the universe has always carried a quiet kind of influence. It never demands attention the way electricity does when sparks fly, or the way the strong nuclear force does when it binds the heart of an atom together with incredible pressure. Gravity does its work slowly, reliably, and often imperceptibly. You can ignore it for most of your life until you drop something, or feel your footing shift, or watch an object fall in exactly the way you expected. It doesn't need to declare itself loudly. It pulls gently, but persistently. This subtle behavior makes the sudden shift near the Planck scale especially striking. It is the one place in physics where gravity stops whispering and begins asserting its presence in a way that cannot be overlooked, even by theories that normally treat it as negligible. To understand why gravity behaves this way, consider first how weak it is in ordinary circumstances. If you compare the strength of gravity between two electrons to the strength of the electromagnetic force between them, gravity is unimaginably weaker. The electromagnetic force outpowers gravity by nearly 40 orders of magnitude. Even between two protons, gravity barely registers. That weakness is why physicists can spend entire careers studying particle interactions without ever worrying about gravity. They work with energies where electromagnetism, strong force, and weak force shape everything, while gravity remains buried beneath all other influences. But gravity is not weak in every context. It is weak only when masses are small or spread out. When mass becomes concentrated, gravity grows dramatically. This growth is non-linear. Doubling the mass doesn't merely double the gravitational pull. Combining masses into a compact region increases the curvature of space in ways that amplify the effect. That curvature deepens, tightens, and eventually overwhelms other influences. This behavior can be seen on large scales when stars collapse into black holes. A star may spend millions of years held up by nuclear pressure and radiation. But when it exhausts its fuel, gravity takes over completely. It crushes the star into a dense remnant. If the mass is high enough, no force can counter gravity, and the collapse becomes unstoppable. This same idea, gravity becoming dominant when mass is concentrated, is essential for understanding why gravity grows loud near the Planck scale. The Planck mass, when squeezed into a region on the order of the Planck length, creates a curvature so intense that space no longer behaves in the smooth, flexible way described by general relativity. Instead, it begins to warp violently. Quantum fluctuations in the geometry, normally small enough to ignore, become significant. The vacuum no longer stays calm, the geometry no longer remains stable, and the gravitational effect itself stops being predictable by classical equations. This is the first sign that gravity is no longer the gentle background force it usually appears to be. The centre of the problem is the relationship between mass, length, and curvature. The Planck mass is defined in such a way that its gravitational radius, the radius at which a horizon might form, matches the Planck length. This means that if you try to localize a mass equal to the Planck mass into a space as small as quantum mechanics requires for that scale, the gravitational pull at that distance would be extreme. Not extreme compared to what we feel, but extreme compared to the strength of all other forces combined. The curvature would be intense enough that the region around the mass would be on the edge of forming a horizon. This raises an important question. How does a horizon form? In general relativity, a horizon appears when the curvature of space-time is so strong that light cannot escape. This requires mass to be concentrated within a specific radius. For massive objects like stars, this radius is large. For tiny objects, the radius is incredibly small. But the principle remains the same. When you compress mass beyond a certain point, gravity's influence grows faster than any other effect. Curvature becomes unavoidable. The structure of space itself rearranges. At the Planck scale, this process becomes complicated because quantum mechanics demands that particles cannot be infinitely localized. If you attempt to confine a particle, you increase its uncertainty and momentum, which increases its energy, which increases the gravitational effect. This feedback loop makes it impossible to ignore gravity near the Planck mass. Instead of being weak, it becomes comparable to or stronger than all the quantum effects that typically dominate small-scale physics. This is one of the reasons physicists say that general relativity and quantum mechanics must converge at the Planck scale. It is not simply because the theories fail mathematically. It is because gravity becomes impossible to separate from quantum behavior. The structure of space-time becomes influenced by quantum fluctuations. The energy associated with uncertainty becomes large enough to bend space. The vacuum becomes dynamic. Even the meaning of distance changes. None of this is visible in everyday life because the energies involved are far beyond anything we encounter. But the mathematics points clearly toward this meeting point. To understand this shift more clearly, think of how each force behaves as energy increases. In particle physics, increasing energy allows you to probe smaller distances. At low energies, forces remain distinct. At higher energies, they begin to merge. Gravity remains weak through most of this process, but at the Planck energy, which corresponds to the Planck mass, gravity unexpectedly joins the conversation. The energy of the system is so high that the force of gravity between particles becomes strong enough to compete directly with the quantum forces. This competition has never been observed in experiments, but it arises naturally from the equations that describe how forces scale with energy. There is another way to see why gravity grows suddenly loud at this scale. Consider the nature of curvature. At ordinary scales, spacetime is almost flat. Even near large planets, the curvature is small. You can live your entire life on Earth and never sense the curvature directly, except through the motion of falling objects. But if you shrink the region you're considering down to extremely small scales, even small masses create significant curvature. And if the mass approaches the Planck mass while the region shrinks toward the Planck length, the curvature becomes so intense that the geometry can no longer remain classical. It begins fluctuating according to quantum rules. These fluctuations are not gentle ripples, they are abrupt changes in the shape of space. At such scales, space may not remain smooth. It may not even remain continuous. It might behave like a network of rapidly shifting relationships, dominated by gravitational influences that change faster than any classical model can describe. In such an environment, gravity cannot be thought of as a static field. It becomes a dynamic player. Another reason gravity becomes dominant in this regime is that the Planck energy is the only energy scale at which gravitational interactions between individual particles become significant. At lower energies, two particles hardly feel gravity. But at the Planck energy, the gravitational force between them becomes strong enough to matter. If the particles collide with energies near this threshold, the curvature created by the impact could be large enough to form a tiny horizon. This is one reason some speculative theories propose that microscopic black holes could form in extremely high-energy collisions, though no evidence for this has been found. An interesting consequence of gravity becoming strong in this way is that even the vacuum state, the lowest energy configuration of space, starts to behave differently. In ordinary quantum field theory, the vacuum is a sea of fluctuations, but the geometry stays fixed. At the Planck scale, the vacuum's fluctuations may contribute to the curvature in significant ways. This means gravity becomes sensitive not only to matter, but also to the quantum fields themselves. The geometry could shift in response to the energy of the vacuum. This is a major clue that a deeper relationship between gravity and quantum mechanics must exist. One of the conceptual challenges here is that we don't have direct experience with a world where gravity is strong at small scales. Our intuition about gravity comes from large-scale objects like planets and stars. We never see gravity acting forcefully in particle interactions. So when theories predict that gravity becomes dominant at extremely small scales, it can feel counterintuitive. But the mathematics is consistent. If you push mass into tiny regions, and if you increase the energy of interactions, gravity grows stronger until it can no longer be treated separately. If this is true, then the Planck scale becomes the natural place to search for a unified description of the forces. It is the point where gravity abandons its usual subtle behaviour and demands equal footing with the quantum forces. This requirement makes the Planck scale both a barrier and an invitation. It is a barrier because our current theories cannot cross it. It is an invitation because it suggests that beyond that barrier lies a deeper structure in the universe. Some theories propose that gravity's change in behaviour reveals something important about its origin. Instead of treating gravity as a fundamental force, these theories treat it as emerging from something more basic. In this view, gravity becomes strong near the Planck scale, not because its nature changes, but because the underlying structure that gives rise to gravity becomes fully visible. The Planck scale would then represent the point where this deeper structure no longer hides behind the smoother behaviour of the forces we observe at low energies. Another perspective considers the possibility that the definition of spacetime loses meaning in this regime. If spacetime is not fundamental, then gravity, which depends on spacetime curvature, must also be emergent. In this view, the loudness of gravity near the Planck scale is not a sign that gravity itself changes, but a sign that the fabric it arises from is changing behaviour. It is similar to how water behaves predictably at large scales, but becomes unpredictable at the molecular level. All of this leads to a picture of the universe where gravity's role changes dramatically depending on scale. At ordinary scales, gravity is gentle. At very small scales, it is forceful. This shift is one of the most important clues physicists have when searching for a deeper theory. Understanding why gravity grows loud at the Planck scale may be essential for understanding why space-time behaves the way it does, why the forces have the strengths they do, and how the universe developed its current structure. Quantum fields usually behave in predictable ways when the energy in a region stays within the limits we're familiar with. They ripple, fluctuate, and interact in patterns that experiments confirm again and again. Their behaviour might seem complicated, but once you learn the rules, they follow them consistently. Each field has a ground state, excitations, vibrations, and interactions that appear in every particle physics experiment we have ever built. The quantum fields that make up our universe have been studied with great detail at energy levels, ranging from nearly zero to the highest we can produce in laboratories. Through all of this, they stay impressively stable, but as soon as you enter territory where gravity begins influencing small-scale behaviour, those fields no longer behave with the calm regularity we expect. They begin to strain under conditions they were never meant to handle alone. The rules that describe their excitations become uncertain, their interactions intensify, their fluctuations grow stronger, and eventually they lose the stability that makes them useful tools for describing particle processes. This difficulty is not because the fields break or collapse, but because gravity pushes them into a regime where their normal mathematical description becomes incomplete. Quantum field theory works beautifully when spacetime behaves like a smooth background. The fields ripple across this background. They interact, decay, and produce new particles. Even vacuum fluctuations behave predictably, with low-energy modes and high-energy modes contributing in ways we can calculate. But beneath these processes is a critical assumption that the geometry of spacetime is stable. The fields require a backdrop, even though it is flexible and dynamic in general relativity. They rely on the idea that on small scales the background remains smooth and continuous. At the Planck scale, that assumption is no longer safe. When mass, energy, or curvature approach Planck-level intensities, space-time itself becomes unreliable. The geometry can fluctuate, the curvature can shift abruptly, distances can change, and the vacuum can no longer be treated as a state with stable properties. Quantum fields depend heavily on the structure of space-time. If the structure becomes unpredictable, the fields must respond to that unpredictability. This is where they begin struggling. To see why this happens, consider what a quantum field is. Instead of imagining particles as tiny points moving around like miniature planets, quantum field theory treats particles as excitations of fields that fill all of space. Each particle type corresponds to a field. Electrons come from the electron field. Photons come from the electromagnetic field. Quarks come from their respective fields. Even the Higgs particle arises from the Higgs field. These fields are not optional. They are the basic ingredients of matter, but their definitions require a smooth arena. Every calculation in quantum field theory assumes that spacetime distances and times can be defined consistently. Even the idea of a particle depends on this. A particle is a ripple of a certain wavelength. If spacetime behaves smoothly, these wavelengths make sense. If spacetime fluctuates violently from one moment to the next, wavelengths lose meaning. This difficulty appears well before the geometry becomes wild enough to form a horizon. Even smaller fluctuations cause the fields to behave unpredictably. A small shift in curvature can change the ground state of a field. A slight change in metric can alter the conditions under which excitations propagate. If these shifts happen rarely, fields can adjust. If they happen constantly, fields cannot settle into stable behaviour. This isn't only a mathematical issue, it reflects something fundamental about how quantum fields work. The fields assume that at very small scales, spacetime looks locally flat. This is the essence of how renormalization works. You take a field that interacts strongly at small distances and define its behaviour by smoothing out or subtracting unwanted infinite contributions. This process works only if the background behaves predictably. If the geometry fluctuates faster than the field can respond, renormalization breaks down. When renormalization breaks down, quantum field theory no longer offers reliable answers. This is not because the field stops existing. It is because the theory describing the field was built using assumptions that no longer apply. Fields don't collapse in a physical sense. Instead, their mathematical description can no longer be trusted. One of the clearest indicators of this breakdown is how vacuum fluctuations behave. In ordinary quantum field theory, the vacuum is not empty. It buzzes with activity. Virtual particles appear and disappear. These fluctuations contribute to measurable effects, such as the Casimir force and the Lamb shift. But these fluctuations are small and controllable in ordinary spacetime. They contribute in predictable ways. Near the Planck scale, vacuum fluctuations may interact with gravitational fluctuations in ways far beyond what the standard theory can handle. The energy associated with vacuum fluctuations becomes large enough to influence curvature. The curvature, in turn, modifies the vacuum. This feedback loop makes the vacuum state unstable. The field can no longer settle into a single ground state. Instead, it may occupy many unstable states that shift rapidly. Another point of difficulty comes from the behaviour of wave packets. A wave packet representing a particle spreads over time. This spreading is predictable when spacetime is smooth. But if spacetime fluctuates, the wave packet can spread in unpredictable ways. It can compress, stretch, or distort depending on how the geometry shifts. If these shifts occur randomly, the motion of the particle becomes impossible to predict with standard equations. This leads to one of the most remarkable implications of the Planck scale. The concept of a particle may not be meaningful there. Particles rely on being able to assign wavelengths and frequencies to excitations. But beneath a certain distance, wavelengths may be meaningless. Instead of particles, what we have are excitations that cannot be resolved into distinct entities. The idea of a discrete particle dissolves into fluctuations of fields that themselves are struggling to stabilize. This difficulty extends to interactions between fields. In ordinary conditions, interactions occur through particle exchange. Fields talk to each other through virtual particles. But if the fields cannot maintain stable excitations, these exchanges become uncertain. The rates of interaction may vary. The strengths of interactions may shift. Even the definition of interaction could become unclear. These problems are not specific to one field or one interaction. They apply across all quantum fields. No matter which field you consider, electromagnetic, weak, strong, fermionic, scalar, they all share the same dependence on the structure of spacetime. When the structure becomes unreliable, the fields do too. This is why quantum field theory loses its calm behaviour at the Planck scale. The Higgs field is an example of how tightly fields depend on the vacuum state. The Higgs field has a non-zero value everywhere in space. This value gives mass to the particles that interact with it. But the Higgs field is sensitive to energy density and curvature. If curvature fluctuates, the value of the Higgs field could fluctuate as well. Even small fluctuations would change the masses of particles. These mass changes would ripple through the structure of interactions, affecting every process involving matter. At the Planck scale, such fluctuations would be unavoidable. Another surprising consequence is the behaviour of gauge fields. Gauge fields have symmetries that protect them from certain instabilities. These symmetries allow for renormalization and ensure that the fields behave predictably. But if spacetime loses continuity, the symmetry may not apply consistently at every point. The field may struggle to maintain the structure that makes gauge theories work. This could cause the breakdown of familiar roles like conserved charges or stable interaction strengths. It's natural to wonder whether any field could remain stable near the Planck scale. From what we know, none of them can. The common thread in all quantum field theories is a reliance on an underlying spacetime with locally consistent properties. When this requirement is removed, everything becomes unstable. The fields may not vanish, but the ability to describe them in the usual way disappears. This is not a failure of quantum field theory as a scientific tool. It is a sign that we have reached the limits of its domain. Every theory has limits. Classical mechanics fails at small scales. Newtonian gravity fails near strong gravitational fields. Quantum field theory fails at the Planck scale. Each failure reveals the need for a deeper theory. The breakdown of quantum fields at the Planck scale is a signal that a theory unifying quantum mechanics and gravity must replace it. This deeper theory must describe both quantum fluctuations and spacetime geometry within a single framework. This need for a unified description is precisely why physicists believe the Planck scale is important. It is where the quantum fields stop being calm. It is where gravity stops being weak. It is where particles lose their identity. It is where space and time lose their smoothness. It is where familiar rules begin dissolving, not because they are wrong, but because they are incomplete. One of the biggest clues comes from the behavior of energy levels in quantum fields. Energy levels depend on the shape of space. If the shape becomes unpredictable, energy levels shift. Shifting energy levels would change particle masses, decay rates, and interactions. Even the vacuum energy could vary. This variation could drive extreme curvature. The cycle continues in a way that amplifies every instability. This amplification is one of the signs that the Planck scale cannot be described by the standard quantum fields. Instead, a different structure must take over. This structure must treat space-time and fields as interconnected. It must allow for fluctuations in geometry. It must account for how energy shapes curvature and how curvature shapes energy. It must allow for fields that cannot be defined through wavelengths alone. It must have a natural way to limit distances and times without relying on smooth geometry. The idea that a particle could become a black hole might sound like a contradiction at first, because we tend to separate these two ideas so sharply in our minds. A particle feels like something tiny, something too small to visualize, something confined to the quantum world where probabilities matter more than shapes. A black hole, by contrast, feels like the opposite. It sounds large, dense, overwhelming, cosmic in scale, and rooted in general relativity rather than quantum mechanics. But when the mass of a particle grows large enough while its size remains small enough, the line dividing these two concepts becomes unclear. The Planck mass sits right at the threshold where this blurring begins. When conditions reach this point, the behaviors we attach to particles and the behaviors we attach to black holes begin to merge, forcing us to think carefully about what each one actually means. To understand how a particle could become a black hole, it helps to recall how black holes form in ordinary astrophysical environments. A star collapses under its own gravity when its internal pressure weakens. If the mass of the collapsing core exceeds a certain threshold, no known force is able to stop the contraction. Gravity pulls inward so strongly that the object's radius becomes smaller than its Schwarzschild radius. Once it crosses this point, the star becomes a black hole. The Schwarzschild radius is not a physical surface but a mathematical threshold. If mass is confined within a region smaller than this radius, the curvature of space-time becomes so intense that nothing, not even light, can escape. This description works well for large objects. The Schwarzschild radius for a massive star is kilometers wide, but the same mathematical relationship applies to any mass. Even small masses have a Schwarzschild radius, although the radius is so tiny that it carries no practical meaning in everyday physics. For an object the size of a proton, the Schwarzschild radius is many orders of magnitude smaller than the proton itself. You cannot compress such an object enough to come close to that boundary under normal circumstances. However, as mass increases, the Schwarzschild radius increases as well, and as the space available to contain the mass shrinks, the energy density grows. In the quantum world, trying to measure the position of a particle requires adding energy. If you attempt to confine a particle into an extremely small region, the uncertainty principle forces the energy to rise. At some point, the energy becomes so high that its gravitational effect must be included in the description. If the energy is pushed far enough, the gravitational radius associated with that energy becomes comparable to the region you are trying to confine. When this happens, you approach the threshold where a particle-like object might collapse into a black hole. The Planck mass marks the point where this threshold becomes significant. If a particle had a mass near the Planck mass and were confined to a region close to the Planck length, its gravitational radius would be nearly the same size as that region. This is the essential condition for forming a black hole. In this sense, the Planck mass represents a limit beyond which the distinction between particles and black holes becomes unclear. This doesn't mean that a particle with the Planck mass automatically becomes a black hole. It means that the gravitational effects become strong enough that the processes governing black hole formation become relevant. This is where theoretical physics begins to encounter difficulties. Quantum mechanics describes particles through wave functions and field excitations. General relativity describes black holes through curvature and horizons. When the conditions allow both descriptions to be relevant, neither theory can be used alone. To understand this better, think of what it means to localize a particle. A particle is described by a wave packet with a certain spread. The narrower the spread, the more precisely we know the position, but narrowing the spread increases the uncertainty and momentum. For very small distances, this uncertainty becomes enormous. The energy associated with that momentum fluctuates intensely. This energy then contributes to the gravitational field, bending space-time in a way that depends on the distribution of energy in the wave packet. This creates a feedback loop. Trying to localize the particle more tightly increases the energy. Increasing the energy increases the curvature. Increasing the curvature changes the effective size of the region that contains the particle. If the energy grows beyond a certain point, the curvature may become so strong that the region behaves like a horizon. The wave packet itself becomes trapped by its own gravitational influence. It can no longer spread in the same way. The particle effectively collapses under the weight of its own uncertainty. This collapse is not the same as what happens to a star. A particle does not collapse because its internal pressure fails. It collapses because the quantum fluctuations required to localize it create enough energy density to curve space-time intensely. This is why the Planck scale is so important. It is the natural limit where quantum localization and gravitational collapse become inseparable. To explore this from another angle, consider the gravitational radius of a mass. For mass m, the Schwarzschild radius is proportional to m. The Planck length, however, is proportional to the square root of the gravitational constant times Planck's constant, divided by the speed of light cubed. When these two scales match, you reach the condition where a particle localized to the Planck length has a mass large enough for its gravitational radius to equal that length. This equality defines the Planck mass. From this point of view, the Planck mass is not a random quantity. It marks the threshold where the gravitational influence of a quantum object reaches the maximum size that quantum mechanics allows for its confinement. Below the Planck mass, the gravitational radius is smaller than the minimal region in which the particle can be localized. Above the Planck mass, the gravitational radius is larger. This means that if you tried to compress a mass larger than the Planck mass into a region smaller than its gravitational radius, the collapse would be unavoidable. This reasoning gives rise to the idea that the Planck mass is the boundary for particle-like behavior. Below this mass, particles behave as quantum excitations. Above this mass, particles behave increasingly like tiny black holes. But this picture is too simplistic. The reality is that neither classical nor quantum descriptions work well near the boundary. Quantum mechanics assumes a fixed background, while general relativity assumes continuous geometry. Both assumptions become unreliable at the Planck scale. This is where theoretical models begin introducing new ideas. Some propose that particles with masses above the Planck mass are not black holes in the usual sense, but behave like quantum black holes. These objects would have horizons, but their horizons would fluctuate due to quantum effects. The horizon might not be a fixed surface, it might be uncertain, it might shift depending on the state of the field. The object might emit radiation through quantum processes. It might not possess a stable identity in the way classical black holes do. Instead of being long-lived cosmic objects, these quantum black holes could exist only for extremely short times. Another idea suggests that a particle cannot have a mass above the Planck mass in the usual sense. Instead, any attempt to assign such a mass automatically produces a gravitational collapse, meaning that nature enforces the Planck mass as a maximum mass for particle-like entities. In this picture, anything heavier must behave as a black hole. These ideas are speculative, but they arise naturally from trying to reconcile the uncertainty principle with gravitational collapse. They also highlight how unstable the boundary between particle and black hole becomes at high energies. A small difference in assumptions can produce different outcomes. Some models predict that a Planck mass object could behave like a heavy particle with unusual properties. Others predict that it would immediately form a black hole. Still others predict intermediate states. One interesting idea is that black holes might not form in the ordinary sense at these scales, because quantum pressure could resist collapse. Unlike classical pressure, which comes from thermal or nuclear interactions, quantum pressure arises from uncertainty. If the uncertainty in momentum becomes large enough, it could counter the gravitational contraction. This would produce a state where collapse is neither complete nor entirely prevented. The object could hover near the threshold in a fluctuating configuration. This idea is similar to how degeneracy pressure supports white dwarfs and neutron stars. In those cases, quantum pressure resists gravitational collapse because particles cannot occupy the same quantum state. At the Planck scale, the relevant pressure would come from uncertainty in both position and momentum. Whether this pressure can balance gravitational collapse remains unknown. Some models say it can, others say it cannot. Another interesting question is whether black holes at the Planck scale could evaporate through Hawking radiation. Hawking radiation arises when quantum fields near a horizon create pairs of particles. One particle falls inside and the other escapes. The escaping particle carries energy away from the black hole. For large black holes, this evaporation is slow. For tiny black holes, the evaporation is fast. For a Planck-scale black hole, the evaporation could be almost instantaneous. This leads to the possibility that a Planck mass particle could collapse into a tiny black hole and evaporate quickly. The evaporation would produce high-energy radiation. The object might not exist long enough to be considered a stable particle. Instead, it might be an intermediate state between particle behavior and complete evaporation. This idea has implications for early universe physics, where energies were high enough to create such objects. It also appears in speculative discussions about high-energy collisions. Another perspective focuses on the geometry itself. If spacetime cannot be defined below the Planck length, then perhaps horizons at that scale behave differently. A horizon might not be a fixed surface. It might be smeared out by quantum fluctuations. The region inside the horizon might not be distinct from the region outside. Instead of forming a classical black hole, the mass might exist in a quantum spacetime foam, where collapse and expansion occur rapidly and repeatedly. This leads to the idea that the distinction between inside and outside loses meaning near the Planck scale. If horizons become fuzzy, then the entire concept of a black hole becomes ambiguous. You might instead have regions where curvature is extremely high, but does not produce a stable horizon. These regions could trap energy briefly before releasing it, or they could exist as transient structures without forming long-lived objects. This ambiguity points to a deeper need for a theory that unifies quantum mechanics and gravity. Without such a theory, we can only speculate about the behaviour of matter near the Planck mass. The key idea is that particles cannot be treated as isolated excitations when their gravitational influence becomes strong, and black holes cannot be treated as classical objects when their mass becomes small. The two descriptions converge. The relationship between energy, length, and the natural limits built into the structure of physics is one of the most revealing parts of the Planck scale story. These three ingredients determine how matter behaves, how space responds, and how the universe sets boundaries that no experiment or calculation can cross without encountering something fundamentally new. Energy determines how sharply you can probe a system. Length determines the scale of the region being investigated, and the limits that arise from their interplay determine how far our theories can be extended before they lose their grip. At everyday scales, these relationships feel smooth and intuitive. As long as distances are large and energies are low compared to their fundamental extremes, the universe behaves in a way that makes sense. But as soon as you begin pushing energy high enough to explore extremely small scales, the stability that frames our understanding begins to weaken. The Planck scale stands as the place where this weakening becomes unavoidable. To see how these ingredients connect, start with the familiar relationship between energy and wavelength. In quantum mechanics, higher energies correspond to shorter wavelengths. A wave with a long wavelength spreads out and does not allow precise localization. A wave with a short wavelength has sharper detail and can probe smaller regions. This connection, which lies at the heart of quantum mechanics, allows us to explore the structure of matter. If you want to examine smaller distances, you must use more energetic probes. This rule applies across all fields and particles. It is why particle accelerators require enormous energies to investigate tiny structures. But even though energy allows you to resolve smaller regions, it brings complications. Energy itself influences the region it enters. A low-energy photon has little impact on the system being observed. A high-energy photon brings intense effects. It alters the behaviour of the field it interacts with. It can excite states that were not accessible at lower energies, and when the energy becomes high enough, it begins interacting with gravity as well. This is where the connection to length becomes non-linear. At some point, increasing energy to see smaller regions begins to distort the region itself. In the familiar range of physics, this feedback does not matter. We can increase energy safely and probe finer details. The region we investigate stays smooth. The energy does not curve space-time. Distances remain fixed. But near the Planck scale, the energy required to probe small distances becomes so intense that the probe itself carries enough energy density to influence the curvature of the region. This creates a fundamental obstacle. The very act of looking pushes the geometry toward instability. The shorter the length you try to measure, the more energy you pour into the system. The more energy you pour in, the more you curve the space. At the Planck length, this process reaches a point where the curvature becomes so strong that the region cannot be probed any further without collapsing or fluctuating unpredictably. This is why the Planck length arises naturally as a limit. It is not a limit imposed externally. It is a limit created by the structure of physics. Energy and length are tied together through quantum mechanics, and gravity amplifies this relationship at extremely small scales. There is no way to separate these ingredients. If we had no gravity, quantum mechanics would allow us to explore arbitrarily small distances. If we had no quantum mechanics, we could measure arbitrarily small distances without injecting energy. But the universe contains both, and together they draw a boundary around what can be meaningfully described. The same logic applies when discussing the Planck mass. A particle with this mass has a gravitational radius comparable to the shortest length scale quantum mechanics allows it to occupy. This is not coincidence. It is a sign that the forces shaping the universe align in a way that creates natural thresholds. When mass grows too large for the region containing it to handle, gravity stops acting quietly. When the energy used to measure a system becomes too high for the region to support, the measurement alters the geometry itself. This dance between energy and length has deeper implications. It suggests that trying to examine the universe beneath a certain scale is like trying to examine the inside of a shadow. The more you illuminate it, the more the thing you're trying to examine changes shape. Instead of yielding finer detail, the region becomes unstable. This does not mean there is nothing beneath the Planck length. It means the tools we use cannot resolve it without altering it. It means our familiar concepts no longer map onto reality in a useful way. Consider again how energy behaves. In particle physics, energy is not just motion. It is also mass, field excitations, vacuum fluctuations, and curvature. When you concentrate energy in a small region, you change the behavior of fields. A high-energy probe can excite hidden modes. It can create particle-antiparticle pairs. It can destabilize vacuum states. These processes add more energy to the region. All of this contributes to the gravitational field. This is why increasing energy to see smaller distances eventually becomes self-defeating. Instead of illuminating finer structure, it generates conditions that overwhelm the region. This is not simply a theoretical inconvenience. It is a clue that the universe has a built-in way of preventing infinite resolution. Without this barrier, physics would contain singularities everywhere. Quantum field theory would diverge uncontrollably. Curvature could increase without bound. Energy could probe infinitely small structures. Nothing would prevent distances from collapsing. But because energy curves space-time, and because quantum mechanics ties energy to localization, the universe prevents infinite detail. This interplay shows up in several places in physics, not just at the Planck scale. Even in black hole thermodynamics, there is a relationship between energy, area, temperature, and curvature. A black hole's temperature increases as its mass decreases. Its entropy is proportional to the area of its horizon. These relationships tie together geometry, energy, and information in a way that hints at deeper constraints. They suggest that the universe stores information in units of area rather than volume. This idea emerges naturally from the dance between energy and length. It also appears in holographic theories, where the information describing a region of space is encoded on a surface surrounding it. But even without these advanced theories, the simple behavior of energy and length near the Planck scale suggests that distances cannot shrink indefinitely. If you attempt to measure a region smaller than the Planck length, the energy involved creates curvature so intense that the region effectively expands again or collapses into something fundamentally different. This is not a sharp cutoff. It is more like a threshold where familiar descriptions stop giving meaningful predictions. Another way to see this interplay is to look at the scattering of particles at high energies. At low energies, scattering can be described using perturbation theory. Particles exchange virtual particles. The probabilities are well behaved. But at extremely high energies, the scattering amplitudes can grow in ways that violate unitarity unless new physics steps in. These violations occur when energy becomes concentrated within a small region. They suggest that the scattering process must be modified at high energies, perhaps by including gravity, perhaps by including new degrees of freedom. Without such modifications, the theory predicts impossible outcomes. Several proposals address this difficulty. One suggests that when energy becomes high enough, it spreads out across additional dimensions. Another suggests that strings rather than point-like particles smear out interactions over finite distances. Yet another suggests that space itself becomes discrete. But all these ideas share something. They agree that energy and length are tied together by limits that cannot be bypassed by increasing energy alone. A particularly striking example of this limit comes from trying to define the position operator in a curved space. In flat space, the position operator has well-defined meaning. But when curvature fluctuates, the uncertainty in position can no longer be separated from the uncertainty in the geometry. The particle may have a position uncertainty, but the space itself also has uncertainty. These uncertainties combine. If they become large enough, they make the position operator effectively undefined. This again shows how energy, length, and geometry interact. Even the vacuum behaves differently under these conditions. In ordinary quantum field theory, the vacuum contains fluctuations at all wavelengths, but the high-energy fluctuations are controlled through renormalization. At the Planck scale, renormalization fails. The high-energy fluctuations become strong enough to influence the curvature. When that curvature changes, the vacuum state changes. The vacuum becomes unstable, which in turn changes the fields that rely on it. This cycle prevents the vacuum from serving as a steady reference. This instability reinforces the idea that distances smaller than the Planck length are not meaningful. If fields and geometry fluctuate uncontrollably, any attempt to define smaller distances becomes impossible. This does not mean the universe ends at that scale. It means that our current tools cannot describe it. Another important aspect of the relationship between energy and length is how it shapes the idea of minimal time. The Planck time is not just a small number. It is the natural time scale associated with the Planck length and the speed of light. It represents the shortest time interval that can be meaningfully discussed. If energy and curvature fluctuate so strongly that distances cannot be defined precisely, then time intervals cannot be defined precisely either. A shorter interval would require localizing processes in smaller regions of space, which would require more energy, which would distort geometry. The result is a limitation on how finely time can be measured. This limitation has implications for causality. If time cannot be subdivided indefinitely, then the ordering of events becomes unclear at very small scales. Events that occur within the Planck time could be indistinguishable. Their sequence might not be well defined. This does not break causality at larger scales. It simply indicates that causality at the smallest scales is not a smooth extension of causality at larger scales. The interplay between energy, length, and fundamental limits also appears in the entropy bounds proposed by various theoretical frameworks. One famous example is the Bekenstein bound, which limits how much information can be stored within a region of given area. The reason this bound exists is tied to black hole formation. If you try to store too much information in a region, the energy density increases. At some point, the region collapses into a black hole. This collapse prevents the information content from exceeding the limit. The bound emerges from the same logic that defines the Planck scales. It shows how energy, curvature, and space place constraints on information. All these relationships hint at the possibility that space and time themselves are emergent rather than fundamental. If geometry becomes undefined beneath the Planck scale, perhaps geometry is a collective behaviour of something deeper. In such a picture, energy and length would not be fundamental variables. They would be derived from more basic components. The Planck limits would emerge from the structure of these components. This idea appears in several quantum gravity models, though none have been experimentally confirmed. The behaviour of space under extreme conditions is one of the most revealing aspects of the Planck scale story. At ordinary scales, we rarely think about space doing anything at all. It feels like an empty stage on which events unfold, something passive, quiet, and stable. Even though general relativity teaches us that space bends and stretches around mass and energy, that curvature is usually gentle. You can live an entire lifetime without ever sensing that the ground beneath you follows a curved trajectory through space-time. Everything seems stable enough that you might never imagine space could tremble, distort, or behave unpredictably. Yet when the energy density in a region approaches the Planck scale, stability becomes impossible. Space no longer behaves the way we expect. Its structure becomes sensitive to even the smallest disturbances. The geometry that once felt enduring begins responding more sharply than any familiar surface. And once space begins to tremble, the rules we rely on for describing motion, energy, and matter no longer hold. To understand why this happens, It helps to start with the fact that space is not a rigid container, it's flexible. General relativity describes space as something that reacts to mass and energy. When mass is present, space curves. When there is motion, the curvature evolves. But these effects are normally so small that even extremely sensitive experiments must be performed to observe them. At our scale, space feels solid and unmoving because the sources that curve it are modest, relative to the size of the region in which they appear. A planet curves the space around it, but the radius of curvature is huge. A star curves space more strongly, but the distance over which the curvature changes is still enormous. These gentle effects make it easy to forget that space reacts continuously to the conditions placed within it. As you push physical conditions to increasingly small scales, the ability of space to remain quiet diminishes. If energy is poured into a tiny region, the effect is not dispersed. The curvature becomes intense because the same amount of influence is exerted across a much smaller area. Even small changes in energy distribution produce noticeable changes in the geometry. This is in contrast to large-scale environments, where redistributing energy rarely produces dramatic effects in curvature. But the most significant transformation occurs when the region being examined shrinks toward the Planck length. At that point, the geometry itself becomes sensitive not only to mass and energy, but also to fluctuations in those quantities. These fluctuations arise from quantum mechanics. At small scales, energy cannot be assigned a precise value without uncertainty. Even in a perfect vacuum, quantum fields generate small bursts of energy. These fluctuations normally have no effect on the geometry, they are too weak. But near the Planck scale, even the smallest fluctuation can generate curvature strong enough to shift the geometry. This sensitivity means the structure of space cannot remain still. It trembles in response to whatever passes through it. It fluctuates because the vacuum fluctuates. It distorts because the fields distort. And once these distortions become strong enough, the concept of a stable geometric background no longer applies. This trembling is not like a vibration in a material. It is not caused by waves passing through a medium. It is a geometric trembling that reflects the instability of distances, angles, and durations. Space stops being a smooth grid. Instead, it behaves like something that responds to every slight change in energy. If the vacuum energy fluctuates, a region of space shifts in shape. If a particle appears briefly, space warps around it. Even if there are no particles, the vacuum itself contains enough fluctuations to keep the geometry unstable. One way to understand this behavior is to consider what it means to measure a distance. In classical physics, distance is a fixed quantity. It can be measured repeatedly with the same result. In quantum mechanics, however, measuring distance at very small scales becomes increasingly uncertain. To measure a very short distance, you must use a high-energy probe. This adds energy to the region. The energy curves the space. The curvature changes the distance. The measurement influences the thing being measured. At small scales, this influence becomes unavoidable. At the Planck scale, it dominates. The trembling of space arises because distances cannot be pinned down. Every attempt to probe them results in further instability. This instability means geometry cannot settle into a steady state. At scales larger than the Planck length, fluctuations average out. Distances remain consistent. Curvature remains smooth. But beneath that scale, averaging becomes impossible. The fluctuations are too large. They no longer represent small corrections. They represent the geometry itself. This leads to a picture of space where smoothness is only an approximation that works at large scales. At very small scales, the approximation falls apart. Many theoretical models explore what this trembling might mean. One idea is that space behaves like a dynamic network. Instead of being a continuous surface, it is made up of discrete connections that rearrange themselves. These connections might stretch, contract, or even change in number depending on the energy present. Another idea proposes that spacetime volumes cannot shrink beyond a certain size. Instead of collapsing indefinitely, the geometry resists further compression through quantum effects. This resistance could create oscillations in the geometry, where attempts to confine space cause it to expand outward again. This behavior can be compared to a system in equilibrium that becomes unstable under pressure. When pushed gently, it holds its form. When squeezed hard enough, it responds with dramatic changes. The trembling of space is not simply a form of motion, but a sign that the structure is becoming too stressed to remain consistent under the rules that apply at larger scales. Even the definition of curvature becomes unclear because curvature requires smoothness. If the geometry fluctuates too rapidly, curvature cannot be defined in the usual way. Another important aspect of this trembling is how it affects the propagation of waves. In ordinary space, waves travel predictably. Light travels at a constant speed. Gravitational waves move through space with well-defined patterns. But if the geometry fluctuates at scales near the Planck length, waves moving through it might experience random distortions. Their paths may shift, their frequencies may change, their phases may scramble. A photon travelling through such a region could experience slight delays or tiny accelerations depending on the exact shape of the geometry it passes through. These effects would be tiny at large scales, but significant near the Planck regime. This trembling also influences the behaviour of particles. A particle moving through unstable geometry cannot maintain a stable wave function. The wave function depends on the underlying structure of space. If that structure changes, the wave function must adjust. But if the changes are too rapid, the wave function cannot adapt smoothly. It becomes uncertain in ways that go beyond ordinary quantum uncertainty. These uncertainties make it difficult to follow a particle's motion. The particle may not have a definite trajectory. It may scatter randomly due to small fluctuations in the geometry. Even its energy may shift unpredictably, because energy depends on the shape of space. This unpredictable behaviour is not a breakdown of physics, but a sign that the tools we use to describe particles are no longer valid at such small scales. Space becomes an active participant in particle behaviour. It does not merely provide a background, it contributes to the motion, the energy, and the stability of particles. This is one of the reasons why unifying quantum mechanics and gravity is essential. Without a unified description, we cannot describe particles in trembling space or space influenced by quantum fields. Another aspect of this trembling concerns the nature of surfaces and boundaries. In classical physics, a boundary is a sharp dividing line. But in a region where geometry fluctuates, boundaries blur. A surface that separates two regions becomes uncertain. It may shift from moment to moment. It may not exist in a stable form. Even horizons, which are normally well defined in general relativity, may become uncertain at these scales. A black hole's horizon could fluctuate, expand, or contract depending on the quantum conditions. The trembling of space could cause the boundary of a black hole to lose its precise shape. This raises questions about how objects form in such an environment. If horizons cannot remain stable, can black holes exist at the Planck scale in the usual sense? Or do they become fuzzy objects with uncertain boundaries? These questions have significant implications for the idea of quantum black holes, which form when particles reach energies near the Planck mass. If space itself cannot stabilize around such objects, their behavior must differ dramatically from the black holes we observe in the cosmos. Another way to understand the trembling is through the idea of minimal length. If space cannot support distances smaller than the Planck length, then the geometry may resist compression. This resistance could create oscillations. When energy attempts to impose a smaller scale, the geometry responds by pushing outward. These oscillations could create a fluctuating environment where distances continually adjust, preventing stability. This effect is similar to how a spring resists compression, but instead of a physical spring, the resistance comes from the structure of quantum geometry. This trembling also affects the behaviour of time. If distances cannot be defined clearly, time intervals lose clarity as well. A clock measuring time depends on stable intervals. But if geometry fluctuates, the clock's intervals become uncertain. This uncertainty is not noticeable at larger scales because fluctuations average out. But near the Planck scale, time itself may not flow smoothly. Processes may not have a clear order. Ordering events becomes impossible. This has consequences for causality. At small scales, events may not follow a strict before and after relationship. This does not violate causality at larger scales. It simply means that causality must be understood differently when approaching the Planck regime. The trembling of space is one of the strongest indications that spacetime is not a fundamental structure. If it were fundamental, we might expect it to behave predictably at all scales. Instead, it becomes unstable at small scales, suggesting that it might arise from something deeper. Perhaps spacetime is emergent, appearing only when many smaller components interact. If this is true, then the trembling reflects the limits of emergence. Beneath those limits, the components behave individually rather than collectively. Geometry becomes a statistical property rather than a fundamental one. Time is one of the most familiar experiences we have, yet it becomes strangely fragile when conditions near the Planck mass are reached. At everyday scales, time behaves so consistently that you rarely have to think about it. Seconds pass at a steady pace. Processes unfold in predictable order. Clocks agree with each other when placed side by side. Even when gravitational or relativistic effects change the flow of time, those changes follow patterns we can calculate with high precision. Time feels reliable, steady and disciplined, guiding everything from the motion of planets to the firing of neurons. But near the Planck scale, this reliability begins to fade. The rules that govern time depend heavily on the geometry of space and the distribution of energy. When those ingredients become unstable, time loses the clarity it enjoys in more familiar environments. Its behaviour shifts in ways that make sequences hard to define, rhythms hard to track, and durations hard to measure. Understanding why time changes so dramatically requires starting with how deeply time is tied to space-time geometry. In general relativity, time is not a separate entity flowing independently from the universe. It is intertwined with space. The geometry of space-time determines how time flows. When space-time curves, time can slow down or speed up. This is why clocks tick slower near massive objects and faster in weaker gravitational fields. Even though this seems unusual from a human perspective, the relationship works consistently across the universe. Time adjusts itself depending on the curvature, and curvature depends on mass and energy. As long as mass and energy remain moderate relative to the scales of the region they occupy, the curvature changes gradually. Time remains well defined. Differences in the rate at which time flows between regions can be calculated. These differences match what we observe with experiments on Earth and observations of distant astronomical objects. The flow of time is not absolute, but is predictable and continuous. Near the Planck scale, however, energy density becomes so high and geometry becomes so unstable that the relationship between curvature and time stops behaving smoothly. Instead of a steady adjustment, the curvature may shift rapidly due to quantum fluctuations. Each fluctuation alters the rate at which time flows. If fluctuations are small and infrequent, time can still be approximated. But at the Planck scale, they occur constantly and intensely enough that time loses its steady rhythm. It becomes sensitive to every slight change in energy. The environment becomes too unpredictable for a single notion of time to remain valid. To see why this happens, it helps to recall how sensitive time is to gravity. Even in everyday astronomical environments, gravity influences time measurably. For example, GPS satellites must correct for the fact that they experience time at a different rate from clocks on Earth's surface. The difference is small but essential for navigation. In stronger gravitational fields, the effect becomes larger. Near a black hole, the difference becomes extreme. Time for someone near the event horizon flows dramatically slower compared to someone far away. This effect arises because mass bends spacetime, and time flows differently depending on how curved the spacetime is. If such differences already exist around ordinary masses, imagine what happens when energy density increases to the point where curvature becomes extreme within a region only slightly larger than the Planck length. The curvature no longer behaves like a smooth surface. Instead, it begins to jump between configurations, reflecting the changing structure of the geometry. Each configuration carries its own rate of time. Since these configurations shift rapidly, time in the region cannot settle into a single pattern. It behaves differently moment to moment. The sequence of events becomes ambiguous. Quantum mechanics adds another layer to this instability. The uncertainty principle teaches that energy cannot be known precisely in small time intervals. High energy fluctuations happen within small regions. These fluctuations affect curvature. Since curvature affects time, the uncertainty in energy becomes uncertainty in the flow of time. The two uncertainties reinforce each other. As energy fluctuates, curvature shifts. As curvature shifts, time fluctuates. As time fluctuates, the way energy evolves changes. This loop makes time behave differently from what we experience at larger scales. This interplay suggests that time is not fundamental in the way we treat it. Instead, time emerges from the underlying structure of space-time, and that structure no longer supports a clear notion of time near the Planck scale. The familiar flow of time may be a large-scale feature that breaks down when quantum gravity becomes important. Several theoretical frameworks propose exactly this. Time may not exist as a single parameter at the smallest scales. Instead, it may emerge from deeper relationships among fields, energy distributions, or geometric structures. One useful way to approach this idea is to consider how time is measured. Measuring time requires a process that changes in a predictable way. A pendulum swings, an atom oscillates, a photon travels between mirrors. These processes rely on stable environments. A pendulum depends on steady gravitational acceleration. Atomic clocks depend on stable quantum states. Photon movements depend on consistent geometry. If the environment is unstable, or if the geometry fluctuates, the process cannot produce consistent intervals. At the Planck scale, the instability of space prevents clocks of any kind from operating reliably. Since no clock can function, the definition of time becomes unclear. Another important difficulty comes from causality. In familiar conditions, events follow sequences. One event happens before another. This ordering allows us to construct timelines. But if time fluctuates rapidly due to changes in curvature, events occurring within tiny regions may not have a clear ordering. One observer might describe two events in one sequence. Another observer might describe them in another sequence. If the underlying geometry is unstable enough, even a single observer might not be able to determine which event came first. This lack of clear sequencing does not affect the macroscopic world, but becomes important when studying interactions at extreme energies. This raises questions about what it means for something to happen near the Planck scale. If events cannot be ordered, then processes may not unfold in the usual way. Instead of a sequence of steps, the process might resemble a fluctuating pattern without a clear temporal direction. Without a consistent ordering, the notion of cause and effect loses precision. Although causality remains intact at larger scales, its fundamental structure becomes uncertain at the Planck scale, because time itself becomes uncertain. These difficulties also affect the basic equations of physics. In classical mechanics, time appears as a parameter that flows independently. In quantum mechanics, time enters the Schrödinger equation as a variable that moves smoothly forward. In general relativity, time becomes part of the geometry. All these descriptions assume that time behaves predictably. At the Planck scale, that assumption fails. the equations cannot operate with fluctuating time, the results become inconsistent. This is one reason why unifying quantum mechanics and gravity is so difficult. One theory treats time as absolute, the other as flexible. Neither treatment works near the Planck mass. Because of this difficulty, some theoretical physicists propose that time might not exist at the deepest levels of nature. Instead, time may emerge from correlations between physical systems. In this view, what we call time arises because states of the universe evolve in a sequence that creates an effective temporal order. If the underlying structure becomes unstable, the emergent time may fail. This would explain why time behaves differently near the Planck scale, without requiring a fundamental time to break. Another idea is that time might exist but behaves discretely rather than continuously. Instead of flowing, time may advance in finite steps. These steps would be so small that they appear continuous at ordinary scales, but become important at the Planck scale. If time cannot be subdivided beyond the Planck time, then events must occur in discrete intervals. Within these intervals, fluctuations could blur the relationship between steps, creating the impression that time is unstable. This idea appears in several quantum gravity models, though no experimental evidence exists yet. Other approaches suggest that time is tied directly to entropy. In this picture, time's arrow emerges from the increase in entropy. But if quantum gravity governs extremely small scales, the notion of entropy may not behave as it does at larger scales. Without a clear direction for entropy, time might lose its direction as well. This again illustrates how time depends on deeper structures. The trembling of space described earlier plays a central role in these ideas. When space fluctuates too rapidly for geometry to remain stable, time cannot anchor itself. If the geometry defining time shifts moment to moment, time becomes an unstable feature of the environment. The fluctuations do not destroy time but prevent it from operating smoothly. They place a limit on how small a time interval can be defined. This instability becomes even more dramatic when considering objects near the Planck mass. If a particle approaches the Planck mass and is confined to a region near the Planck length, its gravitational influence becomes so strong that the curvature fluctuates significantly. The gravitational radius of such an object approaches the region containing it. Time near the object may slow dramatically. But if the boundaries of this region fluctuate, the rate of time may oscillate. The particle might experience stretches of time differently from the surrounding environment. Even the idea of proper time, which is normally defined along a world line, becomes uncertain if the world line itself is unstable due to fluctuations in geometry. Another point to consider is that time dilation becomes more extreme near large curvatures. A small fluctuation in curvature can produce measurable differences in the rate of time flow. Near the Planck scale, fluctuations are not small, they're intense. This means time dilation can shift rapidly. It becomes impossible to track these shifts with a clock. The environment simply does not support a consistent measurement of time. This boundary is not merely theoretical, it influences how we think about the origin of the universe. In the earliest moments after the Big Bang, the universe may have passed through energies near or above the Planck scale. If so, time during those moments may not have flowed in the usual sense. Instead, early cosmic evolution might have occurred without a clear timeline. The emergence of time as a smooth dimension may have happened only later, when the universe cooled enough for geometry to stabilize. This idea shows how important the Planck scale is for cosmology. Without understanding how time behaves under such extreme conditions, we cannot fully explain the earliest moments of cosmic history. If time did not behave normally then, many of the equations we use to describe the evolution of the universe may be incomplete in those early intervals. The implications extend further. If time at the Planck scale loses its familiar structure, the concept of evolution itself must be reconsidered. Processes might not unfold sequentially. They might occur within a framework where temporal order is not well defined. This raises questions about how physical laws function without a clear notion of time. If certain symmetries or relationships appear only when time behaves consistently, those symmetries may be emergent rather than fundamental. Their presence at larger scales does not guarantee their existence near the Planck mass. All these considerations point toward a deeper truth. Time behaves differently near the Planck mass because the environment supporting its familiar behavior collapses. Space becomes unstable. Energy fluctuates wildly. Curvature shifts unpredictably. Clocks cannot function. Sequences lose clarity. And the equations that describe time depend on assumptions that no longer hold. The idea that the universe might contain a flickering, restless layer beneath the smooth structure we normally perceive is one of the most intriguing suggestions to emerge from attempts to understand the Planck scale. At everyday distances, space feels consistent. You can walk across a room, trace a line across a table, or watch light move through a window, and nothing about the environment suggests that the underlying fabric might be unstable. Even at atomic scales, space behaves predictably enough that electrons orbit within well-defined probabilities, and atoms bind together in repeatable patterns. But as soon as you push below these familiar scales, the confidence we place in the quiet stability of reality begins to weaken. When distances approach the Planck length, the smooth backdrop we rely on dissolves into something far more erratic. Instead of a continuous surface, space-time behaves like a fluctuating sea of possibilities. Distances shift, boundaries distort, and the structure that defines geometry begins flickering like a flame under changing wind. This concept, often described as space-time foam, tries to capture what happens when quantum fluctuations become strong enough to reshape the geometry itself. It is not a literal foam with bubbles, nor is it a material substance in the traditional sense. It is a way of expressing how unpredictable space-time becomes when pushed to its smallest meaningful scales. At this level, the geometry does not resemble a smooth fabric. It resembles a restless environment of dynamic configurations emerging and dissolving in extremely short intervals, each one shaped by the intense interplay of quantum uncertainty and gravitational curvature. To appreciate why such a foamy structure appears, it helps to recall how uncertainty grows as distances shrink. The uncertainty principle tells us that the more precisely we try to define a position, the more uncertain the momentum becomes. If you push this idea far enough, the momentum uncertainty becomes extremely large, and momentum corresponds to energy. When energy fluctuates, curvature fluctuates. These shifts in curvature happen in extremely small regions, and because the region is small, even a slight fluctuation can dominate the geometry. This is the central reason why space-time cannot remain calm at the Planck scale. Even in the vacuum, where no particles are present, quantum fields never sit entirely still. They constantly fluctuate, producing pairs of virtual particles that appear briefly before annihilating each other. These fluctuations are harmless at larger scales, because the energy involved is small relative to the region containing them. But when the region shrinks toward the Planck length, each fluctuation becomes intense enough to distort the geometry noticeably. The curvature produced by one fluctuation may reverse as soon as the next one arrives. The result is geometry with no stable configuration. It shifts rapidly, never settling for more than an instant. This kind of environment challenges almost every assumption we make in physics. Geometry is the framework that allows us to define distances, angles, trajectories, and intervals. If the framework fluctuates faster than anything moving through it, then the rules that govern motion lose clarity. A particle travelling through such an environment might experience sudden deviations in its path due to local bursts of curvature. The concept of movement itself becomes blurred. It is not that the particle changes direction due to external forces, but that the space it travels through alters shape unexpectedly. This is very different from turbulence in fluids, which still obey continuous geometry even when chaotic. In fluid turbulence, the underlying space remains stable while the fluid moves unpredictably within it. At the Planck scale, it is the geometry itself that becomes turbulent. There is no stable background. Every point in space may shift relative to every other. Even the idea of a point becomes questionable. If distances cannot be defined precisely, then spatial points cannot be sharply distinguished. To understand this instability, consider what it means to define a line segment between 2 points. At larger scales, the length of the line is fixed, but at the Planck scale, the curvature along the segment may change rapidly. These changes alter the length of the segment. A distance that looks short at one moment may appear longer at another. The geometry oscillates due to vacuum fluctuations that continually reshape it. Because of this, the measured length becomes uncertain. If the uncertainty becomes large enough, the segment loses meaning as a classical distance. The same logic applies to angles and volumes. None of them behave consistently under intense fluctuations. This foamy environment also influences the connection between regions. If curvature changes unpredictably, paths between points may flicker in and out of existence. A path that appears smooth at one moment could twist or pinch at another. In extreme cases, tiny wormhole-like structures might appear. These structures are extremely short-lived. They exist only for times comparable to the Planck time. They are not traversable in the usual sense. Instead, they represent fleeting rearrangements of topology caused by energy fluctuations. Such topological fluctuations, while speculative, illustrate how space might behave when pushed beyond its usual limits. They show that space may not retain a fixed connectivity. It might fluctuate between different configurations in rapid succession. In most models, these configurations average out at larger scales, creating the smooth geometry we observe. But beneath the surface, spacetime remains a dynamic environment with continuously shifting structure. A key point to keep in mind is that this foam-like behavior does not require exotic assumptions. It arises naturally from combining the uncertainty principle with general relativity. The two theories push against each other at the Planck scale. Quantum mechanics demands fluctuations in energy. General relativity says energy curves space-time. When the energy fluctuates strongly in small regions, the curvature fluctuates as well. This feedback loop produces an environment that cannot remain quiet. These fluctuations also challenge how we describe fields. Quantum fields rely on a smooth background to define their excitations. Wavelengths depend on distances. Frequencies depend on intervals. If distances and intervals flicker unpredictably, fields cannot maintain stable excitations. A field that normally supports well-defined particles may instead support unstable, temporary excitations that dissolve quickly. In this environment, particles lose their identity. They become transient features of a fluctuating field. In addition, the foam-like structure complicates the idea of energy conservation. In quantum mechanics, energy can fluctuate as long as it does so for brief intervals. But if space itself fluctuates, the definition of energy becomes ambiguous. Energy depends on the geometry. If the geometry changes rapidly, the assignment of energy to a region may shift unexpectedly. Though global conservation still applies in larger contexts, local conservation becomes complex. Whether this complexity reflects a deeper layer of physics or a conceptual limit of our current theories remains unclear. Another implication of spacetime foam is that particles moving through such environments may experience what appears to be random scattering. Even without encountering other particles, a particle's motion could shift due to changes in geometry. At larger scales, the average path would still appear smooth, but microscopic deviations could accumulate in subtle ways. These deviations might leave signatures in extremely sensitive measurements of high-energy particle behavior, though no such signatures have been detected. The absence of evidence does not rule out the foam-like behavior. It simply reflects the fact that the Planck scale lies far beyond experimental reach. One of the most interesting aspects of this foamy structure is what it suggests about the nature of space itself. If space-time can fluctuate so intensely at small scales, perhaps it is not fundamental. Perhaps it emerges from something deeper. Many theories exploring quantum gravity embrace this possibility. In these theories, space-time is not a continuous surface, but a composite structure built from more elementary components. The foam-like behaviour reflects the dynamic interactions among these components. At large scales, those interactions average out, producing smooth geometry. At small scales, they reveal their underlying complexity. Some approaches propose that space-time arises from a network of relationships rather than points in a continuous space. In this network, the connections between nodes represent geometric relationships. Fluctuations in the network cause fluctuations in geometry. This idea aligns with the foamy behaviour, suggesting that the geometry we perceive is a large-scale approximation of a deeper relational structure. The foam emerges because the network's connections change rapidly when viewed up close. Other theories imagine that space-time derives from quantum entanglement. In this picture, the connectivity of space arises from entangled states linking different regions. If entanglement patterns fluctuate, the geometry fluctuates. This view treats space-time as a byproduct of quantum information rather than a fundamental field. The foam represents unstable entanglement patterns at extremely small scales. Regardless of the framework, the existence of space-time foam highlights the need for a unified theory. Neither classical general relativity nor standard quantum field theory can describe geometry that fluctuates this violently. The foam sits at the boundary where both theories fail. New mathematical tools are required to move beyond speculation. It is important to emphasize that the foam-like behavior does not affect physics at larger scales. The fluctuations average out so effectively that the smooth geometry observed in experiments and everyday experience remains intact. The trembling and flickering occur only when probing lengths near the Planck scale, but their existence reveals that spacetime's reliability depends on scale. Smoothness is not universal, it is an emergent property. Beneath that emergence lies a world that defies classical intuition. Another fascinating implication is how the foam might influence the emergence of classical space-time. If the foam represents the raw behaviour of space-time at small scales, then classical geometry could arise from statistical smoothing. This smoothing process would be similar to how continuous fluids emerge from discrete molecules. At small scales, molecular motion is chaotic. At larger scales, the chaos averages out. The fluid becomes predictable. If space-time behaves similarly, the foam is the microscopic chaos from which geometry emerges. This view helps explain why curvature behaves predictably at larger scales, but unpredictably at the Planck scale. It also explains why time flows smoothly in everyday life, but loses meaning when geometry fluctuates too intensely. The foam may be the source of many features we take for granted. Its dynamic nature sets the stage for the emergence of space, time, and gravity. Many attempts have been made to understand what happens when physics reaches the limits we have been exploring, and none of them arise from guesswork or simple curiosity. They come from necessity. The standard tools we use to describe the universe break down when energies approach the Planck mass, or when distances shrink toward the Planck length. Once familiar rules fail, theorists must ask what deeper rules might take their place. These efforts have produced a range of ideas that seek not only to explain what happens at the boundary where quantum mechanics meets gravity, but also to uncover the structure underlying all of physics. Although these theories differ, they share a common ambition: to create a framework capable of describing a universe where spacetime fluctuates. Particles may collapse into horizons, and the very notion of distance becomes unstable. One of the earliest and most studied approaches tries to frame all particles and forces as manifestations of one deeper structure. String theory is perhaps the best known attempt to do this. Instead of treating particles as point-like, it imagines them as tiny vibrating strands. Each vibration corresponds to a different particle. Light, matter, and forces all arise from variations in the same underlying object. This idea helps solve a long-standing problem. Point-like particles interacting through quantum fields tend to produce infinities that must be removed artificially. Vibrating strings smear out interactions over a finite distance, reducing those infinities. But what makes string theory particularly compelling in the context of the Planck scale is that it doesn't treat gravity as something to be added. It appears naturally. One of the possible vibrations of a string behaves like a graviton, the hypothetical particle that would carry gravitational interactions. This automatic inclusion of gravity makes string theory one of the few frameworks that can describe quantum behavior and gravitational behavior within the same mathematical structure. It suggests that space-time itself might emerge from the interactions of strings. If this is true, the trembling foam beneath reality's surface may represent a fundamental feature of string behavior at extremely small scales. Despite its elegance, string theory introduces challenges. It requires additional dimensions beyond the familiar 3 of space and 1 of time. These dimensions must be compactified, folded into shapes too small to observe. Different ways of folding these dimensions produce different physical outcomes. The challenge lies in determining which compactification matches our universe. There are many possibilities, and distinguishing between them remains an open problem. Although experiments have not yet confirmed string theory, it remains one of the strongest candidates for a theory capable of explaining the extreme behavior found near the Planck scale. Another approach comes from the opposite direction. Instead of beginning with particles and fields, it begins with the geometry of space-time. Loop quantum gravity proposes that space-time is discrete. It breaks the continuum into small units of area and volume. These units interact through mathematical relationships that form a network. This network underlies the smooth geometry we observe at larger scales. If space-time is composed of such discrete units, then the foam-like behavior arises naturally when examining the network up close. The smallest units cannot shrink further. They fluctuate because their connections shift. But the fluctuations average out at larger scales, creating the illusion of continuity. Loop quantum gravity does not attempt to unify all forces in its basic form. Instead, it focuses on quantizing gravity alone. Despite this more focused goal, it captures many features we expect to see near the Planck scale. It predicts that space-time volume cannot collapse to zero. This offers a possible resolution to classical singularities, such as those found in black hole centers or the earliest moments of the universe. Instead of collapsing to a point, a region might reach a minimal volume and then evolve differently. This could prevent the geometric catastrophes predicted by classical general relativity. It also suggests that time may behave differently in these extreme environments, as discussed earlier. There are approaches that attempt to combine aspects of both geometric and particle-based theories. One example is asymptotic safety, which proposes that gravity might become well-behaved at high energies if certain conditions are met. In this framework, the strength of gravitational interactions depends on energy. At low energies, gravity behaves as we observe. At high energies, instead of diverging uncontrollably, the interaction strength might settle into a stable pattern. If this stability exists, then quantum gravity could become predictive without requiring new fundamental constituents of space-time. The foam-like behavior would arise from fluctuations within the gravitational field itself, but these fluctuations would remain controlled by the theory. Causal dynamical triangulations offer another angle. This approach constructs space-time by assembling small building blocks, tiny geometric elements, into larger structures. By summing over all possible ways these blocks can be arranged, the theory seeks a space-time that emerges naturally from the underlying ingredients. Remarkably, when this sum is performed under specific rules, space-time emerges with 4 dimensions at large scales, just like the universe we experience. At small scales, however, the dimensionality appears to change, suggesting a foamy and fluctuating environment. This model treats space-time as something that evolves based on simple rules, similar to how complex patterns emerge from simple interactions in cellular automata. Other theories turn to ideas of symmetry and mathematics. Non-commutative geometry, for instance, begins with the assumption that space-time coordinates do not commute at very small scales. This is analogous to how position and momentum fail to commute in quantum mechanics. If space itself has this property, then the geometry becomes fundamentally uncertain. It naturally leads to a foam-like environment where distances are not sharply defined. This approach provides a way to merge quantum uncertainty with geometric structure without relying on traditional space-time descriptions. Some paths toward quantum gravity attempt to shift our perspective entirely. Instead of treating space-time as something independent, they view it as emerging from relationships among quantum states or from the entanglement patterns that connect them. In these ideas, space arises because certain degrees of freedom become entangled in specific ways. If the entanglement pattern changes, the geometry changes. The foam arises from unstable or rapidly shifting entanglement at small scales. This approach ties information theory deeply into the structure of space-time and connects with ideas developed in black hole thermodynamics. There are also models built around the notion that gravity may not be fundamental at all. Instead, it might emerge from the statistical behavior of microscopic components. In this picture, gravity behaves like thermodynamic pressure or viscosity, properties that appear only when many degrees of freedom interact. At small scales, these interactions fluctuate, producing a foamy environment. At larger scales, the behavior smooths out into the familiar gravitational field. Even beyond these major frameworks, countless ideas attempt to address the gaps left by existing theories. Some explore the possibility of small extra dimensions that alter gravity at short distances. Others imagine that the universe contains hidden symmetries that become visible only at extremely high energies. There are ideas based on spin networks, twistor theory, emergent space-time from condensed matter analogies, holographic dualities, and more. Each one tries to answer the same fundamental questions. What happens when energy becomes too large for smooth geometry to survive? And what structure governs the universe when familiar concepts of space and time break down? The common thread among all these ideas is the acknowledgement that quantum mechanics and general relativity cannot remain separate forever. Each theory works beautifully in its own domain. Quantum mechanics explains small-scale behavior with extraordinary precision. General relativity describes large-scale structure with unmatched elegance. But neither can handle the extreme conditions found near the Planck scale. Theories attempting to bridge the gap must incorporate both sets of ideas. They must allow for uncertainty in geometry, they must allow for curvature to influence quantum states, and they must allow for the vacuum to participate in shaping space-time. These attempts differ in details, but their motivations align. They try to build a description of the universe where particles, forces, space and time arise naturally from deeper principles. Instead of treating these entities separately, they attempt to connect them within a single framework. The foam-like behavior described previously becomes something predicted rather than something mysterious. It emerges as a natural consequence of the underlying structure. Despite decades of work, none of these theories has yet been confirmed experimentally. The energies needed to probe the Planck scale far exceed our current capabilities. This gap between theory and experiment is one of the greatest challenges in modern physics. But it is also one of the reasons why theoretical diversity matters. Without experimental guidance, theorists explore many paths, hoping that one will reveal a structure capable of explaining both the universe we see and the mysteries that lie beneath the surface. It's important to recognize that these theories do not attempt to replace the familiar laws of physics. Instead, they extend them. At large scales, the familiar laws must appear. Quantum mechanics and general relativity must emerge in the limit where fluctuations become small. This requirement serves as a guide. If a theory cannot reproduce the known behavior of the universe at accessible scales, it cannot be correct. This constraint eliminates many possibilities and shapes the search for a successful theory. There is a point in physics where one tiny number, barely noticeable at first glance, begins shaping nearly everything we think we understand about the universe. The Planck mass has this strange kind of influence. It sits quietly as a small value by everyday standards, yet it carries enormous conceptual weight. It defines a threshold where familiar rules stop holding and entirely new behaviour emerges. Even though we cannot reach this mass experimentally, its presence influences theories across almost every domain of physics. It appears in equations describing gravity, quantum mechanics, black holes, cosmology, and even the search for a unified description of nature. Its significance is not that it represents a physical object we can point to, but rather that it marks the boundary of our understanding. To appreciate how deeply the Planck mass shapes our worldview, it helps to consider how physics works far from this boundary. At ordinary scales, you can describe motion using classical mechanics. Forces push and pull objects in predictable ways. Acceleration relates to mass. Gravity keeps everything grounded. Even though the universe is complex, the rules are clear. They hold across a wide range of conditions. Classical mechanics becomes inaccurate at very small scales or very high speeds, but for the world around us, the equations work nearly perfectly. When scales shrink to the size of atoms and molecules, quantum mechanics takes over. In this realm, the rules change. Instead of smooth trajectories, particles become wave-like. Instead of definite outcomes, we get probabilities. Quantum mechanics does not replace classical mechanics arbitrarily. It becomes necessary because classical ideas fail to explain the behaviour of small systems. Yet despite its unfamiliarity, quantum mechanics is incredibly effective. It predicts energy levels, chemical reactions, electrical behaviour, and countless other phenomena with extraordinary accuracy. When moving to cosmological scales, general relativity becomes essential. It describes gravity not as a force, but as the curvature of spacetime. This curvature shapes the motion of planets, stars, galaxies, and even the expansion of the universe. Just as quantum mechanics replaces classical ideas at small scales, general relativity replaces them at large scales. Though its mathematical structure is different from quantum mechanics, it too is highly successful. Observations of gravitational waves, black holes, and cosmic expansion all confirm it. But between these two domains, quantum mechanics on one end and general relativity on the other, stands a region where neither set of rules works. That region is defined by the Planck mass. At masses near this threshold, energy densities become so large and distances so small that quantum mechanics and gravity must both be taken into account. Yet the two theories are based on incompatible assumptions. Quantum mechanics assumes a fixed space-time background. General relativity assumes a continuous geometry. When the background itself begins to fluctuate, neither theory can operate alone. The Planck mass marks the point where their combination becomes unavoidable. Because of this, the Planck mass shapes our understanding of what physics must ultimately become. It tells us that our models are incomplete. It suggests that the universe has a deeper structure beneath the surface we normally study. Any theory hoping to unify the forces must match known behaviour at large scales and reproduce quantum mechanics at small scales. But it must also describe what happens at the Planck mass. This makes the Planck mass a kind of anchor for theoretical physics. It sets the scale where new laws must appear. This influence extends beyond theory into how we interpret observations. For instance, consider black holes. They are classically described using general relativity. Their horizons and singularities emerge naturally from the equations. But near the centre of a black hole, the curvature becomes so extreme that quantum effects cannot be ignored. At those scales, the Planck mass becomes essential. It tells us where new physics begins. Even though we cannot see inside black holes, the fact that general relativity predicts singularities suggests that the theory breaks down. Something else must happen when the curvature becomes large enough. This something else must involve the Planck mass. It may prevent collapse to a point. It may introduce quantum geometric effects that alter the interior structure. It may change the horizon itself. In this way, the Planck mass provides guidance even without observations. It signals where classical concepts must give way to quantum behaviour. The influence of the Planck mass extends to cosmology as well. The early universe passed through energy densities far beyond anything achievable today. As we look back to the first moments after the Big Bang, we eventually reach energies near the Planck scale. Traditional cosmological models cannot describe what happens during or before those moments. The equations for the expansion of the universe break down as time approaches zero. The Planck mass marks the point where a more complete theory must enter. Without understanding behaviour at this scale, we cannot fully explain the origin of the universe. Because cosmology depends so heavily on early universe physics, the Planck mass shapes our interpretations of nearly all cosmic observations. Features such as the cosmic microwave background temperature, the abundance of elements, and the distribution of structures throughout the universe are influenced indirectly by what occurred at early times. If the Planck scale behaviour of space, time, and energy had been different, the universe we observe today would reflect those differences. This sensitivity means that every cosmological observation carries an imprint of the Planck mass, even if the imprint is hidden beneath billions of years of evolution. In particle physics, the Planck mass highlights the limitations of current theories. The Standard Model explains the behaviour of particles extremely well, but leaves several questions unanswered. Why are certain forces weak while others are strong? Why do particle masses take the values they do? Why does gravity remain so much weaker than the other forces? The vast difference between the electroweak scale and the Planck scale is one of the biggest puzzles in physics. This enormous gap shapes how theorists think about new particles and interactions. Any theory explaining why the weak force behaves as it does must also explain why gravity becomes relevant only near the Planck mass. This gap influences ideas such as supersymmetry, extra dimensions, and the possibility that new particles could exist to stabilize the electroweak scale. None of these ideas have been confirmed, but they remain compelling partly because of the structure imposed by the Planck mass. Another aspect influenced by the Planck mass is the concept of minimal length. If distances smaller than the Planck length cannot be meaningfully defined, the Planck mass becomes the mass associated with the smallest resolvable region. This introduces natural limits on measurement, resolution, and localization. It suggests that singularities may not exist in nature. Instead of infinite densities, we may find regions where the geometry resists further compression due to quantum effects. This idea appears in many quantum gravity models, each offering a different mechanism for preventing collapse. But the central point remains. The Planck mass sets the scale where such mechanisms must begin. The Planck mass also shapes how we understand information. In black hole thermodynamics, the entropy of a black hole is proportional to the area of its horizon measured in Planck units. This relationship implies that the Planck area is the fundamental unit of information storage in the universe. If true, then the Planck mass determines how much information can be stored in a given region. It influences discussions of holography, where the information content of a region of space is encoded on its boundary rather than within its volume. This relationship hints at a deeper layer of physics where space, time, matter, and information are intertwined. From a conceptual standpoint, the Planck mass forces us to rethink familiar notions. It challenges the idea that smaller always means simpler. At ordinary scales, exploring smaller structures reveals finer details. But at the Planck scale, smaller structures become more complex rather than less. Distances lose meaning. Time fluctuates. Geometry changes. Energy and curvature influence each other so strongly that new rules must appear. The Planck mass marks the tipping point where reductionism falters. Instead of peeling away layers to reach simpler constituents, we find a chaotic environment where familiar categories blur. This change in perspective influences how physicists imagine the fundamental building blocks of reality. If the Planck mass marks a limit, then perhaps elementary particles are not tiny objects, but excitations of fields or network nodes in deeper structures. Perhaps space-time is not fundamental but emergent. Perhaps the laws of physics themselves arise from patterns that only stabilize at larger scales. In these ideas, the Planck mass becomes not just a numerical boundary, but a philosophical one. The presence of the Planck mass also shapes expectations for future experiments. Even though we cannot reach this scale directly, we look for indirect clues. High-energy cosmic rays, gravitational wave signatures, black hole behavior, and deviations in particle interactions all offer potential hints of Planck-scale physics. Theories that predict observable deviations must be consistent with the Planck mass. Experiments that look for new effects often reference the Planck scale as a benchmark for determining sensitivity. The Planck mass shapes our understanding by reminding us that physics, as complete as it seems, remains unfinished. It highlights the boundary between knowledge and speculation. It marks the region where familiar laws work beautifully, and the region where deeper laws must take over. Instead of acting as a final answer, it points toward a greater theory. It is a scale that signals where unification must occur, where geometry must become quantum, and where the distinction between matter, space, and time must be reconsidered. There comes a point in any exploration of the universe's deepest limits when you feel the need to return to gentler territory, not because the mysteries beyond the Planck scale lose their fascination, but because perspective is only complete when you reconnect the extreme with the ordinary. After spending so much time at the boundary where space-time trembles, particles threaten to collapse into horizons, geometry dissolves into a flickering foam, and the very meaning of time grows uncertain, it becomes almost surprising to remember just how calm the universe feels at human sizes. The contrast is so sharp that it helps illuminate what makes our everyday world as stable as it is. The descent back to familiar scales is not a retreat from complexity, but a rediscovery of why the ordinary laws of physics work so well, and why, despite all the strangeness hidden beneath them, we can trust the world around us to behave in ways that feel consistent and predictable. One of the most striking realizations in stepping away from the Planck frontier is how forgiving the physical world becomes once we move to larger distances and lower energies. The violent fluctuations that dominate the Planck regime soften almost immediately as scales increase. The geometry that once pulsed unpredictably settles into a smooth surface. Quantum fields that struggled to remain stable regain their calm behavior. Time, which faltered under intense curvature, flows reliably again. Even the vacuum returns to being a steady foundation, rather than a restless environment of wild fluctuations. This gradual reappearance of stability is not merely comforting. It reveals how the laws of physics emerge from deeper principles only when the universe provides enough room for those principles to average out. This transition begins with the geometry itself. At extremely small scales, curvature responds to tiny fluctuations in energy, and the space around those fluctuations shifts rapidly. But as the scales grow, each fluctuation becomes less significant relative to the size of the region. Instead of dominating the geometry, fluctuations blend into the background. The curvature smooths out, and space-time becomes a reliable structure once again. This smoothing is not an accident. It reflects a statistical truth. Unstable behavior at small scales averages into stability at larger ones. Just as air made of countless vibrating molecules feels soft and continuous rather than jittery and discrete, space-time made of countless microscopic interactions appears smooth once you take a step back. The same kind of stabilization happens among quantum fields. Near the Planck scale, fields cannot define consistent excitations. Their wavelengths become meaningless when distances flicker, but once space-time geometry regains its steadiness, the fields regain their ability to support well-defined vibrations. Particles reappear as recognizable excitations of their fields. The uncertainty principle still holds, but it no longer drives runaway curvature. Instead, it shapes particles' behavior without destabilizing the geometry. The vacuum fluctuations remain, yet they no longer influence the structure of space-time in dramatic ways. They become small, predictable contributions just like they appear in everyday quantum mechanics. Time is another beneficiary of this return to stability. At the Planck scale, even simple questions such as which event happened first become difficult to answer. But as soon as curvature calms, time resumes its familiar role. Clocks begin ticking at steady rates. Events unfold sequentially. Cause and effect regain clarity. The Planck time remains an important conceptual boundary, but above that scale, time becomes reliable enough to allow everything from orbital mechanics to biological rhythms to unfold without interruption. This transition highlights how dependent time is on geometry. Once geometry stops fluctuating unpredictably, time emerges again as a dependable dimension. As we continue stepping back from the Planck regime, the forces we know also re-establish themselves. Gravity, which had grown overwhelmingly strong at tiny scales, weakens rapidly as distances increase. Soon it returns to being the gentlest of the forces, shaping large-scale structures without interfering with the behavior of particles. The strong and weak nuclear forces resume their familiar roles inside atomic nuclei, while electromagnetism governs the interactions that allow atoms to bond, molecules to form, and matter to behave as it does on human scales. The dramatic competition among forces that arises near the Planck energy disappears entirely once the energy drops. The hierarchy among forces comes back into order, and the world behaves the way we expect. This descent also restores the clarity of particles themselves. At extreme energies, particles may blur into quantum black holes, or dissolve into unstable excitations with no consistent identity. But at lower energies, they return to being well-defined entities. Electrons have clear masses and charges. Photons carry energy predictably. Neutrinos move through matter in ways that match experimental observations. These behaviors are not arbitrary. They arise from the way quantum fields stabilize at larger scales. Particles become reliable because the environment that supports them becomes predictable. It is helpful to imagine this descent not as leaving behind the Planck scale mysteries, but as allowing those mysteries to recede into the background so the familiar framework of physics can return. In a sense, the world we know is made possible precisely because the Planck scale chaos remains confined to scales so small that its effects average out. The stability of matter, the consistency of gravity, the flow of time, and the coherence of space all rely on the fact that we live far above the energies and densities where instability reigns. The Planck mass reveals the threshold where the chaos begins, but it also highlights how far we are from that threshold in our everyday lives. As we return to the scales of atoms, one of the first things to notice is how quantum mechanics becomes dominant while gravity becomes negligible. This separation is essential. It allows atoms to form stable configurations and chemical bonds to exist. Without this hierarchy, the delicate balance that allows matter to organize itself into structures like DNA, rocks, stars, and living organisms would be impossible. The Planck mass sets the scale beyond which gravity disrupts these configurations. But far below that scale, quantum mechanics governs without significant gravitational interference. Going further into the macroscopic world, quantum behavior fades in direct observability. Objects become large enough that their quantum fluctuations average out. You do not see interference patterns in cars or chairs. You do not find objects spontaneously tunneling across rooms or spreading into superpositions visible to the naked eye. These phenomena do occur in principle, but at scales extremely difficult to access. Decoherence ensures that quantum behavior remains visible mainly in controlled laboratory conditions. Still, the laws governing the quantum world underpin everything in the macroscopic world. The return to these scales highlights how two regimes, quantum and classical, fit together seamlessly despite arising from very different underlying principles. Stepping even further back, we reach the gravitational domain where general relativity shines. At planetary scales, gravity dominates motion. The Earth's orbit, the Moon's movement, and the trajectories of satellites all follow the curvature of space-time. Unlike the turbulent curvature near the Planck scale, the curvature here is smooth, predictable, and calculable with precision. This is where Einstein's equations describe reality beautifully. Black holes, neutron stars, and gravitational waves all appear naturally from the mathematics. Yet even these dramatic objects exist far below the regime where quantum gravity takes over. Their curvatures, though strong, remain smooth enough that space-time does not fluctuate unpredictably. The Planck scale foam stays hidden deep below them. The farther we move from the Planck regime, the more the universe reveals its layered structure. At the scale of solar systems, physics becomes classical again. Forces and motions follow familiar patterns. At the scale of galaxies, gravity arranges stars into spirals and clusters. At the scale of the cosmos itself, dark matter and dark energy influence the expansion and structure of the universe. All these behaviours rely on the smoothness of space-time at large scales. What becomes clear in this descent is that the Planck mass not only defines the upper boundary of our understanding, but also sets the lower boundary for the stability that makes the macroscopic universe possible. Everything above that threshold gains coherence. Everything below it dissolves into fluctuation. This contrast clarifies why the universe is neither chaotic at large scales nor perfectly smooth at all scales. It occupies a balanced middle ground where stability and complexity coexist. As we return fully to the world we know, the world of seconds ticking, objects falling, light reflecting, waves moving through air, and people navigating their surroundings, we regain the sense of normalcy that physics at extreme scales temporarily removes. The Planck scale remains important in shaping what is possible, but it stays hidden from our senses and our daily experience. It guides the foundations of physics without intruding on the calm behaviour of the universe we inhabit. In this gradual return, something else becomes evident. Understanding the Planck scale enriches the experience of the everyday world. Knowing that beneath each atom lies a depth of behaviour so extreme that space-time itself trembles gives a new appreciation for how remarkable stability truly is. The fact that we can move through space without fear of sudden geometric collapse, that clocks can measure time reliably, and that forces act consistently is something easily taken for granted. Yet these everyday certainties rely on the universe keeping us far from energies and curvatures that would disrupt them. This perspective also highlights how physics operates with layered rules. At one scale, general relativity builds the architecture of the cosmos. At another scale, quantum mechanics builds the structure of matter. At yet another, statistical mechanics describes how large groups of particles behave. And underlying all of it, the Planck scale sits as the boundary where a deeper rule must exist. These layers do not conflict. They complement each other, each emerging where the universe allows it to work reliably. The Planck mass may govern scales we never directly touch, yet its influence helps shape the very world we move through every day.